So is the screen visible?
Yes, sir. Yes, sir, it is visible.
It says unsupervised neural machine translation.
Yes, sir. Yes, sir.
Okay. Okay, let's begin. So I guess this is the first tutorial of ICON 2020 being organized in IIT Patna. The topic is extremely timely. This is unsupervised neural machine translation. There is no doubt that machine translation has been a very important application of AI, and whole of NLP started with machine translation when English to Russian and Russian to English translation became important in the 60s. And since then, many paradigms have come in machine translation. Today's paradigm is neural. But neural machine translation is very data hungry. You do not have so much of data. So what can we do to still do machine translation through neural network? And the extreme form of low resource will be unsupervised neural machine translation, where there is no parallel data. So anyway, all this will get unfolded as we go ahead with the tutorial. So I'm Pushpak Bhattacharyya. I'm a faculty member in IIT Bombay. And I'll be covering the first part of the tutorial, giving the introductory remarks and covering different paradigms of machine translation. Other tutorial presenters are Jyotsana, Diptesh, and Tamali, who are PhD students in IIT Bombay, CSE department in our lab called Center for Indian Language Technology. Diptesh has finished his PhD, waiting for his defense. He will be joining postdoctoral research in England. And the other member of the team is Dr. Rudra Murthy, who did his PhD in IIT Bombay, CSE department, and now is with IBM. So let's get started. I'll start with the paradigms of machine translation. Now, this is the perspective. This view of natural language processing is now well accepted. That natural language processing happens in layers, starting with morphological processing, where the words are broken into morphemes. Then part of speech tagging is done when the grammatical categories of words are obtained, noun, verb, adjective, and so on. Chunking gives the short phrases, the little boy, for example. Parsing produces the syntactic tree. Semantics does word sense disambiguation and semantic role identification, agent, object, instrument, and so on. And finally, many sentences are stitched together to form a paragraph, and the meaning understanding of the paragraph involves obtaining the meanings of sentences, phrases, words, and stitching them together. So this has the three basic problem of coherence, cohesion, and coherence, cohesion, and also different kind of co-referencing. So these three C's are important when we do discourse. Now, all these are relevant to machine translation also. You will see that as we go ahead with the discussion, one of the approaches to machine translation insists on going through this whole NLP pipeline and obtaining a representation from the source sentence, which is then passed through a generation algorithm to produce the target sentence. So this is the NLP pipeline, or NLP stack as it is popularly called. And there are many platforms which provide tools, resources, NLTK, for example, for doing all these tasks. Natural language processing is also a multidimensional problem, and these three axes are important: the language axis, the problem axis, and the algorithm axis. Now, this three-dimensional picture can be adapted to machine translation also, where the language axis will become language pair, say English, French, Hindi, Marathi. And the problem will be a specific problem with respect to machine translation, maybe the alignment problem, how you align the phrases and the words. And the algorithm axis is giving the technique for solving that problem, let's say alignment. So this is the big picture in which the machine translation problem is also set. Translating from one language to another by a computer is the crux of the problem of machine translation. Now, if you look at this taxonomical diagram, machine translation has, first of all, two basic approaches: knowledge-based approach and the data-driven approach. So until lots of parallel corpora became available, the only methodology was knowledge-based. Okay, we give rules for translation. So that's why it is called rule-based machine translation. And the two branches of rule-based machine translation are interlingua-based and transfer-based. We'll see the relationship between interlingua and transfer, the essential points of their similarity and difference. However, since 1980s, slowly beginning in 1980 and now being the ruling paradigm is the data-driven approach. So first data-driven approach again was mooted in 1980s through what is called EBMT, example-based machine translation. And this made use of analogy or similarity. We have a part in the discussion on EBMT. But gradually, the approach that overtook the field is statistical machine translation, SMT. And the essence of SMT was alignment, which we'll again discuss. And SMT in 2016 gave way to neural machine translation when Google showed that neural machine translation was giving much better accuracy, much higher quality of translation over SMT. And this happened because gradually the amount of parallel corpus increased. And it was found that as a technique, neural machine translation was able to exploit these huge amount of data much better than statistical machine translation. We will have an insight into why, as the data increases, neural machine translation begins to score over SMT. That's a very interesting point of insight. Okay, so this is the book I wrote in 2015 on machine translation, where you can see the reflection of this taxonomy except for the neural part. So the book covers up to statistical machine translation, and probably a new edition of the book will cover neural also. Now, today's ruling paradigm is neural machine translation, which is very, very data intensive. This is an interesting diagram from Philip Cohen and Rebecca Noel's paper in 2017, which showed that neural machine translation begins modestly with small accuracy, but see the rate of increase in accuracy. The y-axis is blue score, and when the data begins to increase, the neural machine translation overtakes rule-based, the blue line, or the phrase-based system. which is again statistical, sorry, and the phrase-based with big language model. Big language model is brought into picture in the decoding stage, where the phrase table entries are combined together to produce the target language sentence. So you can see that from maybe about 10,008, 10 to the power 8 words, that's about 100 million words, the neural machine translation exceeds the accuracy of statistical machine translation. Are my slides visible? Can somebody verify?
Yes, sir.
Yes, sir.
Now, it is interesting that the essential elements of machine translation paradigms are all words starting with A. That was something which was interesting for me. In rule-based machine translation, analysis is the watchword. We do the source language sentence analysis properly, then we have done more than half the job. The crux of the matter in statistical machine translation, the foundation of statistical machine translation is alignment. In example-based machine translation, we make use of analogy or similarity. And in neural machine translation, most probably, again, another A word is essential, namely attention. Now, why is machine translation difficult? What is the problem that we are tackling in machine translation? We are tackling the problem of language divergence. So languages have different ways of expressing meaning, and this is called divergence problem. There are two kinds of divergence: lexico-semantic divergence and structural divergence. So in 2002, we wrote a paper which is well cited. This is on English to Indian language divergence, and the case study was English-Hindi machine translation. The reason why this study has remained relevant and important is that it brings to light different gaps that have to be closed for English to Indian language machine translation. So one of the gaps, for example, is the word order. English is SVO, verb comes in the middle. Hindi is SOV, verb goes to the end. So this gap or divergence needs to be closed either by writing a rule or by training a machine through statistical means or training a machine through neural means. Now, very briefly, lexico-semantic divergence arises from difference in the word. So boy and ladka are two different words. This is a very trivial example of lexical divergence. Semantic divergence is the same word can mean two different things in two different languages. Our popular example always is shiksha, which means education in Hindi and punishment in Marathi. Structural divergence is the divergence of word order, phrase order, and so on to the school. See, the preposition comes before school. School ko comes after school in Hindi. So preposition becomes postposition. So structural divergence is referring to the syntactic differences. Lexicosemantic divergence refers to the meaning difference, pragmatic difference, word difference, and so on. A very nice example of that is difference in proverbs, for example. In English, a bad workman quarrels with the tools becomes nach na jane angan tera in Hindi. Both mean the same thing, but the imagery is very different. In English, the picture is of a workman using a set of tools. In Hindi, the picture is of a dancer finding fault with the floor. So these are difference or divergence issues which machine translation needs to close. So throughout the tutorial, I think if you keep this point in mind, that it is the language divergence which is the crux of the matter, and all paradigms of machine translation essentially are looking for techniques for solving this divergence, then I think all the discussions will fall in place and will make sense. So by way of illustrating the issue of divergence, we take this sentence, this blanket is very soft. English sentence, this blanket is very soft. The corresponding Hindi is, यह कंबल बहुत नरम है. यह कंबल बहुत नरम है. Bengali is, এই কম্বলটি খুব নরম. Marathi is, हा कंबल खूप नरम आहे. Manipuri is, कंपर आसी mon mon lawi. So I purposefully chose these languages. English is Indo-European, Hindi is Indo-Aryan, Bangla is Indo-Aryan with Tibeto-Burman influence. So there is influence from northeastern languages. Marathi is Indo-Aryan, but with Dravidian influence. It is close to South India. Manipuri is actually a Tibeto-Burman language spoken in the northeastern part of the country. And see how they express the same meaning differently, very, very interesting. For English, the intensifier is very, very soft. This very has become bahut in Hindi, which is fine. Khub in Bengali, fine. Khup in Marathi, again fine. So very, bahut, khub, and khup are all adverbs qualifying an adjective. See the interesting divergence in Manipuri. Mon mon is reduplication, doubling of the word. So very soft is becoming mon mon, soft soft. So this is a characteristic of Tibeto-Burman languages. You see it in Indonesian also. So how the intensifying adverb is dealt with is a matter of the language property. And while English, Hindi, Bangla, and Marathi have similar behavior, an adverb intensifying an adjective, Manipuri has a very different behavior because it is from a different family. It is simply repeating the adjective to convey the notion of adverbial intensification. Look at other phenomena. Auxiliary verb is. This is in the middle of English sentence. It has gone to the end in Hindi sentence, which is in consistency with the property of SVO, SOV divergence. Same thing happens in Marathi, hai and ahe. Bengali, interestingly, doesn't use copula verb. There is null here. So the auxiliary has disappeared in Bengali when you go from English to Bengali. Interestingly, Manipuri has brought back the auxiliary lawi, and again at the end of the sentence, just like in Hindi and Marathi. The word this is yaha, a, and ha in Marathi. Again, Manipuri has a slight difference. This yaha, a, ha, they are all before the noun. Manipuri puts this after the noun. So you can see Manipuri is indeed a different member. It belongs to a different class. Bengali also has its own points of difference. First of all, it did not have copula, hai, ahe. Interestingly, Bengali speakers in North India who have grown in the north tend to put a copula verb at the end of a Bengali sentence also. Ei kombolti khub norom hocche. They would say hocche. Okay, hai. And then the interesting classifier T, which no other language uses. This is most likely, again, an influence from Austroasiatic language family. It's called a classifier. So the point I'm making through this very, very important slide is that languages have these kind of differences, and rule-based machine translation went into those fine details of this difference and gave rules for covering this gap. So an example of that is Sistrans machine translation system, where each pair of machine translation language has close to 100,000 to 200,000 rules. And this is one of the best performing machine translation systems, which took many, many, many years to build because of the number of rules. So this distance between languages can be diagrammatically depicted. Hindi is at the root, and I'm interested in finding out Hindi's distance with other languages. Hindi is close to Marathi indeed, slightly more distant from Bengali, quite distant from Manipuri, and indeed very distant from English because of the family difference. Now, back in 1968, Vauquois, who was a physicist in France, gave an abstraction of machine translation paradigms and techniques. So this is a famous diagram called the Vauquois triangle, also called Vauquois pyramid, where the left-hand side refers to analysis of the source sentence, right-hand side refers to generation of the target language sentence. So if the source sentence is English, this blanket is very soft. On the Hindi side, we'll have yah kambal bahut naram hai through generation process. Now, the analysis can be done up to a stage which shows the point of transfer. So analysis, transfer, and generation. These are the three basic steps in all machine translation. And from which level you begin to transfer decides what kind of paradigm you are operating with. When languages are very close to each other, where almost word-to-word substitution will give you the translation, you don't need any analysis. So you can go from the bottom of the triangle to the other side. At the highest level is the deep understanding level, where the source sentence is completely disambiguated, and the word meanings, semantic roles, phrases, everything has been disambiguated. We have got a meaning graph. From the meaning graph, we produce the target language sentence. And this kind of transfer diagram, or the Vauquois triangle, is quite complex. Vauquois thought about many different situations of transferring, which we can understand more simply through a simplified Vauquois triangle, where analysis and generation happens, and in between, this horizontal yellow line is called transfer, ATG. Again, let us remember ATG, analysis, transfer, and generation. Different paradigms handle these three tasks differently. So we have said in rule-based machine translation, there are two branches, interlingual and transfer-based. And if we remember that the whole main point of machine translation is managing the language divergence and closing this gap, then we understand the difference between interlingual and transfer-based machine translation. In transfer-based machine translation, we can decide how much of analysis we want to do on the source sentence. At what point can we begin to transit to the target language? Let's take this Hindi sentence, Raja ko naman karo. The English sentence will be give obeisance to the king. Marathi is Raja la naman kara. Tamil will be Arasarai Vananku. Manipuri is Ning Thobu Khoiramu. Okay, so we have chosen 5 languages: Hindi, Marathi, English, Marathi, Tamil, and Manipuri. Now, the transfer amongst these different language families can be understood by understanding the micro tasks which are involved. Give obeisance to the king is the sentence. Give obeisance is the verb phrase. To the king is a noun chunk. Give obeisance becomes naman karo in Hindi, naman kara in Marathi, vananku in Tamil, and Manipuri is khoirummu. Inflected noun will be to the king, Raja ko, Rajala, Arasarai, and Ningtho. So Namankaro and Namankara are very close to each other. Vananku is distant, Khoirammu is again distant, but Tamil and Manipuri have similar behavior. Vananku and Khoirammu. Arasarai and Ningthobu, again similar behavior. Raja La is attached to Raja. Arasarai is also one word. Raja ko are two different words in Hindi. To the king is three words. Okay, so this is known as agglutination, where Arasarai, Ningthombu, Rajala are gluing the morphemes together. So since Namankaro and Namankara are almost same, this is like word-to-word substitution. So here the closing of divergence is achieved by very minimal effort. More work is required to transfer to Marathi from Hindi. Raja ko and Raja la. Ko will become la, but you will have to also join la with Raja. Okay. And then Tamil Vananku Namankaro, a single word. Vananku is single word representing two words in English, Hindi, and Marathi. Arasarai is also a joined word. So this clearly shows that Hindi and Marathi will require less work to close the divergence. Tamil will require more work. Manipuri also will require more work. English, of course, will require more work because Raja ko, postposition, gives rise to a preposition in Hindi, in English. So if I do a transfer rule study, then from this parse tree of give obeisance to the king, I have to do obeisance give the king to. Okay, that will be the first transfer rule, inverting the verb compound and inverting the constituents of the preposition phrase. After that, we have to do stitching together if the target language demands it. But for Marathi and Hindi, hardly anything will be required. We simply have to invert, and to the king will have to be joined together in Rajala. So that's what is done in rule-based machine translation. The source text goes through the whole NLP stack: morphology analysis, pause tagging, chunking, vibhakti computation, named entity recognition, word sense disambiguation. And then we transfer to the generation side. We'll do lexical transfer. That means get the words of the target language, achieve agreement. Okay, larka khana khaya, larke ne khana khaya. Okay, so ne introduces a different form of larka. Then intra-chunk relations, inter-chunk relations, and then word generation. Intra-chunk and intra-chunk relations are different kinds of semantic roles or dependencies which are introduced. Okay, so this is the basic step of rule-based machine translation. And some of the things are not required depending on how close the languages are. Okay, words and disambiguation may not be required if the two languages have a lot of shared vocabulary. Now we come to the data-driven side, statistical machine translation. The ideal statistical machine translation was conceived with no need for any analysis. So you can go from the left-hand side to the right-hand side at the bottom of the triangle. No analysis required. That was the ideal statistical machine translation. But as we proceed with the discussion, we'll see that that is really an idealization. The foundation for statistical machine translation is this argmax expression. Given a French sentence F, we want the best possible English sentence E. French and English are only by way of example. F is source language, E is target language. But let's stick to French and English. That's how the original paper was written. So it is an argmax on E. That means output that English sentence which has the maximum probability given the source sentence F. You apply Bayes theorem and then we obtain argmax on E, but with a different probability expression. Probability of E given F has become probability of F given E, the likelihood part, and the prior probability has been isolated, PE. So the statistical SMT works with these two parameters. PE is called the language model probability. PF given E is called the translation model probability. Now, these are probabilities, so they have to be obtained from the data. Those values have to be obtained from the data. And we apply maximum likelihood principle. So the probabilities are obtained by different counts given in the data. So probability of W3 given W1 and W2 is obtained from counting how many times W1, W2, and W3 appear together, divided by the count of W1 and W2. So all probabilities are computed from counts in the corpus. So this shows that clearly we need data. Now, how do we get probability of F given E? Clearly, maximum likelihood estimate will ask us to do count of F and E divided by count of E. But here comes a problem. F and E are complete sentences, and it is quite possible that F and E do not appear together in the sentence. Okay, India's foreign policy was studied closely. Right? So this particular sentence may not appear as such in the training data. So how do I get the count? So there we have a very classic strategy. We do back off. That means do not do the count of the whole entity, but break it into its parts and then try to try to predict the count by decoding methods. So again comes a difficulty. You can break the sentence into its parts. And I have the sentence in source language and the target language sentence parallel to each other by means of training example. And I've already understood that I have to work with smaller parts, not the whole sentences. Then comes the notion of alignment. India's foreign policy was studied. Bharat ki Videsh Niti. Now, Bharat corresponds to India, Videsh Niti, foreign policy. But how do I know that India corresponds to Bharat, foreign policy corresponds to Videsh Niti? How do I know that? This is the notion of alignment. So we have to solve the alignment problem. Probability allows us a very nice method of doing this. Since alignment is a hidden variable influencing the translation process, we can uncover it by introducing A, the random variable of alignment, in the probability expression and marginalize through A. So this is a very standard probability process, marginalization. And then we apply chain rule, okay, of probability to uncover the alignment. So Ram went to school, Ram Pathshala gaya. Here the alignment is Ram to Hindi Ram, went to gaya, to nothing, school Pathshala. So this alignment gets uncovered by means of a probabilistic treatment whereby a random variable of alignment is introduced to marginalization, random variable of length m is introduced to marginalization, and then apply chain rule. So this gave rise to 5 different models which came from IBM in 1980s. This was a paradigm changing work. And model 1, model 2 up to model 3 have remained very popular. 4 and 5 have become interesting pieces of history because they're very complex. And here I show the derivation of this expression involving alignment. These are essentially probability steps, marginalization, and then chain rule, then applying independence assumptions. So the heart of the matter is alignment, and we take inspiration from what happens in our two eyes. Whenever we look at a picture, two images form in the two retina of the eye, two eyes. So this is the picture. The left eye sees two chairs, a table, and a flower vase. Right eye also sees them, and then chair one must be mapped to chair one in the right eye. Chair two to chair two, table to table, flower vase to flower vase. So this kind of alignment from a larger picture to components of the picture is solved in the brain by running an alignment algorithm, most probably. So alignment is very fundamental to many NLP tasks: spell checking, translation, transliteration, speech to text, text to speech. And from word alignment, we go to phrase alignment, tree alignment, and factor-based alignment, all of which have enriched statistical machine translation. But everything came from this 1990 paper from IBM, Brown et al., and later refined by Oak and Nee, 1993. So quickly, an example of alignment. We have three rabbits, Troya Lapa, rabbits of Grenoble, Lapa de Grenoble. We have two sentences in English and French, and they're in alignment. The sentences are in alignment. Sometimes sentences also may not be in alignment. So this is the parallel corpus, very small parallel corpus, but illustrates the point. So for alignment, we start with uniform probability. Each word on the English side or French side can map to all the other words, all the words in the target side. So we start with uniform probability of mapping. Then we make use of the expectation maximization algorithm. We obtain the count of these mappings, okay, W going to A in the sentence AB going to WX, okay, 3 going to Troya in French from the parallel sentences, 3 rabbits mapping to Troya Lapa. So this is obtained by means of probability values, and from this expected count, we produce what is called the counts table for each of the parallel corpus sentence, each pair of sentence. From this expected count, we can obtain the revised probability of mapping. So we are essentially running an expectation maximization algorithm. So when we do that, the probabilities get revised. You can see from everything was 1/4 in the first row. Now this is revised to half and half. This is 0 because these two words C and D are off Grenoble, D Grenoble. They are not there for in the first sentence, which contains the word 3. Okay, 3 rabbits, Troya Lapa. So automatically, because of this EM algorithm, the table shows that 3 cannot map to off or Grenoble, D Grenoble. We continue this way, keep on revising the counts and revising the probabilities, and ultimately we get an alignment table of words. And this is absolutely the fundamental and most important step in statistical machine translation. Now, what is the theoretical basis of this? The theoretical basis of this is mapping of vocabulary of language 1 to language 2 based on mapping of sentences given as training data in the parallel corpus. So what is in a name? Naam mein kya hai? That is one parallel sentence. That which we call rose by any other name will smell as sweet. This is my second parallel corpus. So we collect the vocabulary, that is the dictionary words. Then we see the correspondences. We have sentences on the English side denoted by E, sentences on the French side denoted as F, And then we have hidden variable. The hidden variable are alignments with respect to sentences. The parameters are mapping of probabilities, mapping of dictionary words by probability. So the likelihood expression is created based on these probabilities. We take log likelihood because working with exponent is cumbersome. We take expected value of the data likelihood. Then we introduce the constraint. Every word on the English side should map to all words in the French side with different probabilities. The probability can be 0. So for every English word, I have one constraint. So I goes from 1 to vocabulary of English. Inside J goes from 1 to vocabulary of French. These lambda i's are Lagrangians. So after we set up this constraint equation, we differentiate with respect to the parameters equate to 0. And after that, we obtain the probability of the dictionary mapping, which is our ultimate aim, in terms of the alignments within the sentences. Alignments within the sentences are expressed in terms of vocabulary mapping and the probabilities. So this is a coupled equation, M step and E step, and the classic EM algorithm that gives rise to the word alignment. So this is the foundation for statistical machine translation. When statistical machine translation was becoming important, we undertook a task in our lab at IIT Bombay. We, fortunately at that time, through ministry's assistance, parallel corpora became available in multiple Indian languages. Though it was small, some 50,000 sentences, but we ran experiments for different pairs of languages. In the blue region of the table, you can see high blue scores. In the yellow region, it is lower. In the green region, it is very low. And in the brown region, it is also moderate. So the blue region is North Indo-Aryan to Indo-Aryan machine translation. You can see that you can have as high blue score as almost 70 for Hindi and Punjabi. Hindi Marathi is also very good. 39 is very good blue score. Marathi to Hindi is 45. That was the kind of blue scores we are getting. But when we went to Dravidian languages, let's say Hindi to Tamil, Telugu, Malayalam, blue scores were 14, 21, 10, much lower than what we observed for Hindi to other North Indian languages. Similarly, going from Dravidian languages to Dravidian languages, small blue score, Dravidian languages to Indo-Aryan languages, relatively higher blue score, but nothing compared to what we see in the whole Indo-Aryan family. But this was a very useful exercise, and it showed that we could quickly build statistical machine translation systems, even based on small amount of parallel corpus. Now, this was the experience of statistical machine translation. EBMT has historical importance because that was the first attempt at data-driven machine translation. And it was based on a very nice insight from a very well-known NLP researcher, machine translation researcher, Makoto Nagao from Japan. So he said that man doesn't translate a simple sentence by doing deep linguistic analysis. Deep linguistic analysis is needed in role-based machine translation. Rather, man does the translation first by properly decomposing an input sentence into certain fragmental phrases, very often into case frame units, and then translating. Okay, this was very insightful, which said that you have to break the sentence into parts, achieve translation, and then combine the translation. That you see is the main idea in encoder-decoder, the decoding stage in SMT. Okay, that was quite prophetic, looking into the future. So he continued by translating these fragmental phrases into other language phrases, and finally by properly composing these fragmental translations into one long sentence. The translation of each fragmental phrase will be done by the analogy translation principle with proper examples as its reference. So EBMT had this paradigm: take the source sentence, match its parts with existing translations, do alignment, and then generate the sentence. Okay, And if you have exact match of the source sentence in the database, you output the target text immediately. Now, analogy is the crux of the matter, and it needs similarity. So we need resources and means for measuring similarity. Now, there are different ways of measuring text similarity. There is bag of words based, permutation based, n-gram based, vector based, tree based, semantic graph based, and feature based. These days, we can compute similarity through language models, which again are vectors from deep learning systems. So one of the important similarity measures is the BLUE scores, which evaluates a machine translation output against a reference translation. And the main idea there is matching the n-grams from the two sentences and scoring the similarity. The feature-based similarity computation is also very rich. We can take features like length, whether the sentence is active or passive. We can take the parse tree, concatenation of vectors of words, bag of words, position of nouns, etc., etc. So many similarity features are taken. Main verb, for example, is an important similarity feature. We can go to complex knowledge bases, the frames, for example, and take those. So this way we can take the feature similarities, give them weightage, combine the feature similarities to give the similarity of the whole phrase with another phrase or a whole sentence with another sentence. And this can be done by a regressor, for example. EBMT also does decoding. It does many important operations like null adaptation, reinstantiation, abstraction, and respecialization, case-based substitution, semantic graph, or graph parse substitution. So I illustrate this generation process by a sentence. Suppose a new sentence comes. Tomorrow, today will be yesterday. Okay, tomorrow, today will be yesterday. And a closed sentence which was found in the database. The database contains parallel translations. A closed sentence was found, which is yesterday, today was tomorrow. Yesterday, today was tomorrow. So what is the difference between these two sentences? Very little. Only was and will be. Otherwise, tomorrow, today, yesterday, they appear in both sentences. Only their positions are different. So a similarity computation module will say that amongst all the sentences, parallel sentences present in the database, this is a good candidate for proceeding further. So, kal, aj, kal, tha. This is the parallel Hindi sentence. And yesterday, today, tomorrow was. Kal is ambiguous in Hindi, standing for both yesterday and tomorrow. Now we cannibalize, that is, we take parts of this sentence and obtain their translations. And by adjusting the difference in the predicates and matching the arguments, the translation is obtained as kal, aj, kal hoga. Tomorrow, today will become tomorrow. Okay, or today will become tomorrow. So kal, aj, kal hoga. So this is called reinstantiation using the translated fragments in the target sentence. So this is exactly the idea which carried through in statistical and neural machine translation. So the neural machine translation, which will be covered through unsupervised neural machine translation in detail, the basic paradigm is encoder-decoder. I read the book. You get the encoding of the sentence at the end of this RNN, LSTM, whatever. And then this encoding passes through a decoder, which is again a sequential machine. And out comes the Hindi sentence, Maine kitab padhi. I read the book, Maine kitab padhi. So this is a vector representation coming out of the encoder, processed in the decoder to produce the sentence. Now, some representative accuracy figures have been reported for Indian languages neural machine translation. Hindi Marathi, we have observed, gives a BLUE score of 31, Hindi Punjabi 63, Punjabi Hindi 68. Because Punjabi Hindi is almost word-to-word substitution. Even the suffixes and the post positions are almost one-to-one mapping. Hindi Gujarati also is very high. Gujarati Hindi is also high. So I think it is a good idea now to compare and contrast these different paradigms of machine translation. This is illustrated with the translation of the verb has. Peter has a house, Peter has a brother, this hotel has a museum. So English uses the same word has, but the translations are very different. So if I take English Marathi translation, Peter has a house is Peter kade ek ghar ahe. Peter has a brother, Peter la ek bhau ahe. See the suffix changes. This hotel has a museum. Here hotel madhye ek sangrahalay ahe. So ahe is same everywhere, but the suffix is changing from sentence to sentence. Kade, la, and madhye. So have is always a tricky case for English to any other language translation. So rule-based machine translation will have to give rules of this kind. If the syntactic subject is animate and syntactic object is owned by a subject, then have should translate to kade. Okay, Peter has a house. Peter has a house. Peter has a car. Here there is ownership. But Peter has a brother? No, Peter doesn't own a brother. If the syntactic subject is animate and the syntactic object denotes a kinship subject, there is a relation, kinship relation, then have should translate to la and ahe. If the syntactic subject is inanimate, hotel has a swimming pool, then the have should translate to madhye ahe. Okay, so these kind of rules have to be written. And the Sistran, which was mentioned before, had about 100,000, 200,000 rules created this way, considering all possible situations. And there is this additional complexity. How do you know which rule applies in this particular situation? And if multiple rules apply, which one should we choose? Okay, so all these decision questions are solved very nicely in data-driven machine translation because the data tells you what to do. Okay, the rules are good, but when it comes to choosing a particular rule and deciding which rule applies, the data implicitly gives you that guidance. So in ABMT, we'll have X have Y going to X kade Y ahe, X la Y ahe, X madhya Y ahe, and one of these rules will apply in the current situation. In SMT, on the other hand, we'll have these parallel phrases: has a house, kade ek ghar ahe, has a car, kade ek gadi ahe, has a brother, has a sister, hotel has, hospital has, where we see evidence of kade, la, madhye, all these appearing in the parallel sentences. Then we apply alignment, we obtain the phrase correspondences with probabilities. And when a new sentence comes, this hospital has 100 beds. We extract n-grams from this sentence, and these n-grams translations are obtained from the phrase table, which was created by alignment. And then we apply the decoding algorithm. That is how statistical machine translation works. So what I wanted to say there was that in rule-based machine translation, you will have to anticipate all situation and give rules. In statistical, we will have to construct the phrase table mappings and use those phrases. And example-based machine translation, we will have to again take similarity of the sentence and take parts of the similar sentence and use them. In neural, we pass the whole sentence, get an encoding, and then produce the target sentence through decoding. Now, in Indian language, natural language processing, there are many challenges. Moreover, there is a resource scarcity. There are 22 major languages in India written in 13 scripts. There are over 720 dialects. Code mixing often happens, and in a very interesting way. Kyun ye hesitation? Kyun ye Hindi? Hesitation is English. This very interesting gerandification happens. Gadi chalawing. Gadi chalana Hindi. Ing is English suffix. There is absence of basic NLP tools and resources. There is absence of linguistic tradition for many languages. For example, Andamanese languages, not everything has been worked out, for example, as far as linguistic theory is concerned. So we wrote this paper in 2019 to discuss the challenges of Indian language computing. Script complexity is high. There is non-standard transliteration. Mango can be AM, AAM on capital AM. The storage is non-standard. Not everybody uses Unicode storage. There are language phenomena which are challenging. For example, khasparna in Hindi. In Bengali, it is heshe otha. So Hindi is laugh and fall. Bengali is laugh and rise. Morphological stacking can happen, ghada samurchani, resource scarcity is of course there, which is why unsupervised methods have to be seriously studied. And the resource problem can be mitigated by artificially boosting the resource using subword based NLP. We break the word into its parts and get the translations. Then we can take help from another language. This is called cooperative NLP. We can use higher level language properties like part of speech, sense ID, etc. But there is always this NLP's law of trade-off. You can have trade-off between precision and recall, sparsity and ambiguity, information injection versus topic drift. So when we use subword-based machine translation, we had these blue scores from our earlier work in statistical machine translation. When we use subwords like characters, morphemes, syllables, orthographic syllables, and especially byte pair encoding, we could achieve improvement over our previous figures for all language pairs. For example, Punjabi Hindi was already high. There we got 2% improvement because the baseline was already very high. But Punjabi Bengali, there was 10% improvement. On the Dravidian side, which was a headache, where we had to use subwording. We had to break the word into its parts because Dravidian languages are morphologically complex. They use very high scale of agglutination. There we had improvements of 20%, 15%, 18%. So okay, Telugu to Gujarati, for example, showed about 19% improvement. So this was because of morphology breaking of the words, morphological breaking. If we use byte pair encoding, then you can see Telugu Gujarati shows 25% improvement. Okay, so this was a statistical subwording technique, will be used in neural quite a lot. Then we could use linguistic embellishments. Instead of working with I ate mangoes, we embellish the sentence with semantic role, agent, past tense information, plural information, morphological and semantic role information. So this kind of enriched parallel corpora with linguistics is also applied in neural machine translation, because the neural machine translation paradigm is very data hungry. If we use linguistic embellishments, the data requirement goes down. So we did this exercise back in 2010, and we could improve the performance over baseline by many blue points. So baseline raw parallel corpora gave us 24 blue score. With linguistic embellishment, we could go up to 28. Then we also used operative natural language processing, pivot-based machine translation. So there we showed that if we use pivoting, so for example, pani to jal, Hindi to Bengali, that translation is not available in the training corpus. But we have pani to water and water to jal. So I can make use of English as a via media called pivot language or assisting language for translation. So this we did for a number of interesting situations. And always the idea was same. You have the source and pivot phrase table, pivot and target phrase table, and you also have source to pivot phrase table. And everywhere probability plays a role as to which pair we should choose from where. We ran experiments on Mauritian to English machine translation through French as assisting language. And even with small amount of corpus, we could see that the performance improves by about 2 to 3 blue points from Mauritian Creole to English. The last bar is the final accuracy on Mauritian Creole to English. For English, this English to Hindi machine translation, we also use pivoting, and all these graphs which gradually go up and up. Okay, you take any amount of corpus, let's say 7,000 sentences, then introducing pivots, we can take the accuracy up to the final figure, which is at the highest level, and all because of pivoting, that is introducing an assisting language. So this was also a trick for solving the data sparsity problem. And neural Indian language machine translation, our strategy has been phrase table injection using statistical machine translation, word going as feature, morphology segments going as features. And we have done extensive experiments on this, on basic bi-LSTM encoder-decoder, and also on transformer architecture. All this is supervised with parallel corpus, and this will set the stage for unsupervised neural machine translation. So here I'd like to point to the English to Marathi neural machine translation blue score on the basic vanilla system, just with parallel corpus and nothing else. We got blue score of 10.79. When we introduced more corpus, we got 14.51. And when we introduced different kinds of byte pair encoding, 14.63. With more byte pair encoding experiments, we could go up to 16.73. With back translation and forward translation, 16.47. And when we introduced phrase tables as part of corpus from the statistical machine translation, we could reach a blue score of 21.05. So all this is consolidated, and 21.91 is the figure which is obtained through different kinds of enrichments of neural machine translation. So sample outputs also show that we do pretty well on English to Marathi as well as Hindi to Marathi machine translation. Of great interest are these morphologically rich phenomena, Mahima Madhye, okay, um, such campaigns, for example, Yuvak becoming Tarun in our output, Tarun in Google Translate. In Bing translation also, there is Tarun. So extensive experimentation and observations have been done. So the summary is that in this part of the tutorial, we discussed different paradigms of machine translation. And data-driven machine translations are statistical and neural in nature. There are many tricks which can be used for resource mitigation. Unsupervised neural machine translation is to be taken very seriously. It is happening all over the world. And the experience of Indian language neural machine translation shows us that we have to use many tricks along with the parallel data. And resource mitigation tricks are the following. We can inject phrase table. We can harness monolingual data with back translation, which will be covered going forward. And enhancements like morphological and word feature injection also are important. So final message on this introduction part is that NLP has to deal with this trade-off. We cannot indiscriminately increase one input because that can have effect on other inputs. So if we take too much of subwords, for example, then it can introduce ambiguity. And if we have too little of it, then we have to be aware of the sparsity problem. So a kind of middle path has to be taken, which was also propagated by Lord Buddha. So this, all these concepts which I have said are linked from my homepage, and the lab in IIT Bombay has many resources for a very long time, since 2000, which are used in machine translation. So now I'll pass the baton to other tutorial presenters for covering unsupervised neural machine translation. If there are one or two quick questions, we can take that here.
Yes, sir. May I read out the questions, please?
Yeah.
Hi. So Vishwajit asks, what is the current state of ongoing work on machine translation, keeping Sanskrit as one of the language pairs?
Yeah. So Sanskrit is very interesting because almost all languages in India have descended from Sanskrit. So there is quite a lot of vocabulary overlap, and Shiksha, for example, comes from Sanskrit. So we can take advantage of vocabulary overlap. But the difficulty with Sanskrit is that Sanskrit uses heavy samas and sandhi. So lots of words are joined together. Okay, Raja ka Adesh. In Sanskrit, preferred expression will be Raja Adesh. You combine them and also then apply sandhi. So you need robust segmentation rules, and that will break the long strings into small parts. The other point is that Sanskrit is not really a language of day-to-day use. So this work of using Sanskrit in the machine translation framework is not at the highest level of priority, but it has utility if we want to exploit the vocabulary overlap.
Vishwajit has a follow-up question. Can it be overcome with NMT?
Can what be overcome with NMT?
This problem of heavy segmentation and requirement
I
of
see.
segmentation.
Yeah, that's an important point. So we use byte pair encoding, for example, and byte pair encoding isolates the commonly occurring substrings and translates them. So yes, that is a possibility.
Few more questions. Should I read them out?
Yeah, very quickly maybe. If
Okay.
something takes time, then we can take it
Yeah.
at the end of it.
Question 2, how much blue is efficient with Indic languages and with low profile languages? Which measures or functions to consider, preferably with Indic languages?
So I'll quickly give the answer, and it requires more discussion. Quick answer is that we apply blue score, but we apply subword based blue score. Okay, not on the whole sentence and whole words, but break the words into parts and then apply blue score.
Right. Follow-up, does higher inflection in words affects efficiency of translation?
Yes, if you're going from, remember the Vokwa triangle and the language divergence. If the languages are distant, then inflection can interfere with the translation quality.
Sarvesh asks, what is the best evaluation method for MT, especially for Indian languages, because there are criticisms about blue?
Yes, so the answer is again subword based blue.
Okay, that's it. These are the questions.
Okay, thank you. So tutorial can continue. I have unshared my screen.
Is my screen visible, everyone? And am I audible?
Yes, sir.
Yes, sir.
Okay, great. Hi, I'm Diptesh Kanojia. Professor Pushpak has already introduced me. So please allow me to start by discussing the needs for the supervised NMT paradigm. Although Professor Pushpak has already explained in comprehensive detail as to what these needs are, I would still like to go over these in brief and discuss the very need of an unsupervised paradigm for the task of neural machine translation. So statistical methods for machine translation, or MT as we call it, require a large set of sentence pairs in two languages. This resource in our experience is a must to build a decent translation system. Such bilingual data is scarce for most language pairs, and moreover, the quality of this data varies largely over different domains. So for example, if you were to, let us say, use a parallel corpus from the agriculture domain to train the translation system, you might not get a decent output on a set of test sentences from the tourism domain. Domain similarity, or rather a certain amount of domain or vocabulary overlap, is essential because this parallel corpus also helps populate the vocabulary for the target language model. Neural machine translation, or NMT, which is the standard paradigm of MT these days, has been claimed to suffer from the data scarcity more severely than the phrase-based MT. And its hunger is not easily satisfied, and thus resource scarcity becomes more of a problem. A gold standard parallel corpora requires expert annotators to sit for hours and provide adequate and fluent translations to source-side sentences. Sometimes comparable parallel corpora is edited to generate such a gold standard resource. In both these cases, however, the annotators suffer a lot of cognitive load, which I can vouch for, because if your spouse has been a translator, you are often at the receiving end of the irritability this can cause. But moving on. Unsupervised NMT, which trains a neural translation model only with monolingual corpora, was proposed for those scenarios which lack bilingual data or parallel corpora. So it would be a bit of a stretch to say that we could use this paradigm when an alien race finally arrives at the end of 2020 to complete this beautiful year that has been. But it is true that this paradigm indeed does not need parallel corpora, so one can simply start with monolingual corpora. Despite its progress in research, the performance of the unsupervised methods has been evaluated mostly on high resource language pairs. So for example, German to English, vice versa, or French to English and vice versa. So for these language pairs, huge amounts of parallel corpora is already available. However, the unsupervised scenario does require large monolingual corpus for both the source and the target language sites. So it also requires a decent quality of cross-lingual word embeddings, that is mapped word representations from both the languages in a common space. And unsupervised learning is an extreme scenario of empty machine translation where bilingual information is very weak. So to supplement the weak and noisy training signal, knowledge transfer and regularization are crucial, which can be achieved by the bidirectional sharing. It is based on the fact that translation problem is basically dual in nature. So source to target and target to source tasks are conceptually related to each other. Please also take note that the network sharing is less effective among linguistically distinct languages in MT. So as Professor Pushpak said, the languages which are more distant from each other. So the resource requirement for unsupervised NMT still remains a challenge for many low resource language pairs, especially for many Indic languages, where even a decent size of monolingual corpus is hard to obtain. These resource constraints have daunted the NLP community for various tasks. Low resource Indic languages, which include the likes of Sanskrit, Manipuri, Oriya, Khasi, Bodo, etc., still do not have large monolingual corpus publicly available for research. If we discuss the older languages such as Hebrew, Greek, and Latin, it would open a different can of worms altogether. And then we have obscure languages such as Sentinelese, Ugaritic, etc., where no corpus is available, and one might not even find annotators for creating such resources easily. So in such scenarios, for building a translation system, unsupervised machine translation can be really helpful, can be pivotal, and may indeed prove resourceful if one is looking for at least vague translations from one language to another. So what would you need to build such an unsupervised neural translation system? Despite the fact that unsupervised learning for NMT assumes no bilingual data for training, one still requires a decent size of monolingual corpus from both the languages. And apart from that, now here is where things get a little tricky. One would need, or should I say, decent, or should I say accurate cross-lingual word representations. To get these word or phrase mappings for the NMT task, these embedding models can be trained if you have parallel word mappings in a small amount, a dictionary of sorts. So one could arguably use unsupervised methods to generate this small amount of mapping as well. Or you could provide a dictionary, a manually generated word mapping list, or manually built word mapping list, where human supervision ensures the quality for the generation of this resource. So these representations form the very crux of unsupervised neural machine translation paradigm. And as most of us would know, word representations, whether monolingual or cross-lingual, are at the helm of most of the NLP tasks. Now let us discuss some foundational aspects required in this tutorial before we move on to the various approaches of the UNMT paradigm. I will discuss cross-lingual word embeddings and then hand over the stage to Jyotsana. Please allow me to digress a little. So if we look at, since we were talking about word representations, if we look towards the psycholinguistics literature, word representations create a mental image for human beings. So the acquisition of information and creation of mental representation occurs in a two-step process. So as per research conducted by Ramos et al. In 2014, a human being needs a sufficiently complex brain structure to first establish the internal brain state, which is capable of co-varying with external events. That is a sound mind which is able to understand the external events that are going on, which are happening around the said human being. And the second step is where our interest lies, the validity of meanings for any concept or word representation is gradually achieved by confronting the world with the environment in which it was spoken. So, which means that the word must be taken along with sufficient amount of context, which helps a human being render a meaning to it. So this context for humans is usually derived not just by reading the word, but can also be available to the human brain based on previously acquired world knowledge. Moving on to what machines do and taking a huge leap or a jump towards cross-lingual word representation, these embeddings are generated based on two monolingual corpora available to a machine. So cross-lingual word embeddings have shown to be effectively learning bilingual word representations, and the underlying idea is to independently train the embeddings in different languages using monolingual corpora first, and then map them to a shared space through linear transformation. There are some assumptions here when such word embedding models are generated. So for instance, the English numbers and animals as shown in the image show a similar, that is a isomorphic geometric structure with their Spanish counterparts. So if we look at the image, the English word cat is close to its Spanish counterpart catu. Similarly, MEOW meow in English is closer to MIAU meow in Spanish. Here, one assumes the isomorphic properties of relations between words, and one can also say meow and meow are cognates. And for any two languages which are in question, or the ones for which cross-lingual word embeddings are being generated, the geometric relations that hold between words are similar across languages. Eventually, the aim of cross-lingual embeddings is to generate a vector space based on a linear projection with a transformation matrix of words W source mapped to target. One can transform the vector space of a source language S to the vector space of the target language T using this linear projection, and thus use this for the task of translation. There are various approaches available to generate cross-lingual word embeddings. The three main sets of methodologies are mapping based, then you have the joint loss based, where a joint loss function is computed, and a pseudo multilingual corpora based. So under the mapping based set of methodologies, you have the popular ones like VecMap, Muse, GeoMM, RCSLS. Among the joint loss based methods, you have joint replace approach, and the joint matrix factorization based approach. And then for the set of methodologies which are based on pseudo multilingual corpora, you have random translation replacement approach and the multilingual clustering based approach. In the interest of time, I would only go into the details of a few of these approaches, but let us first have a look at what mapping based approaches do in general, which are currently the most commonly used methods. So the mapping based approach requires one to first train monolingual embeddings for the individual languages on both the source and target sites. Let us say X represents the vectors from the source side language embedding and Y represent the vectors from the target side language embeddings. In this case, we show example words from English and Hindi languages in the X and Y clusters. The mapping which is learned is based on a linear transformation. This approach creates a transformation matrix where the goal is to either generate X is equal to WY or Y is equal to WX, depending on which side is being projected onto the other. Commonly, the target language side is mapped onto the source, thus making your compute objective Y is equal to WX. Let's now look at some of the approaches. Okay, so Muse is a tool which is publicly available to create such representations. It allows one to learn the mapping Y is equal to XW. It was released by Facebook AI Research in 2017. As discussed, given the target vector Y and the source vector X, Muse learns a mapping Y is equal to XW between the two spaces. It trains a discriminator to tell whether two vectors are from the same language and a generator to map the vectors from one language into another. Using adversarial learning, the approach learns a rotation matrix W, which roughly aligns the two representations. The mapping W is further refined via procrusts. It does this in such a way that the distribution of vectors in each of the two languages is the same. So the discriminator and the generator here are adversaries, and they each train and try to beat the other. So for the translation task, however, they compute something called cross-domain similarity local scaling, or CSLS as they call it, using the k nearest neighbor algorithm. For a more detailed discussion of this approach, we suggest you go through the paper by Conojia et al. Referred in this slide. And as shown in the image, there are example words from the English language in the X cluster and from the Italian language in the Y cluster. As you can see, the authors try to show that the words cat and gatto are similar to each other across languages. One can also say that these words belong to the category of genetic cognates, but that is a whole other discussion. Eventually, Muse is able to provide modified word representations for words from both the sides in two different files. So pragmatically speaking, if you're using this tool, you'll get two different files, which one can then use in any subsequent NLP task. And the toolkit itself supports the tasks of word analogy and translation without any parallel data. This toolkit supports both a supervised and unsupervised approach for generating your cross-lingual embeddings. Moving on to the next approach, that is WebMap. So the underlying idea behind this approach is more or less similar to the previously explained approach Muse. So please just allow me to simply discuss the differences. So this particular approach starts with a pre-processing that length normalizes the embeddings, then mean centers each dimension, and then length normalizes the monolingual embeddings again. They say that the second length normalization guarantees that the final embeddings have a unit length. So as a result, the dot product of any two embeddings is equivalent to their cosine similarity and thus directly related to their Euclidean distance. So this approach uses a fully unsupervised initialization. So the underlying difficulty of the mapping problem in this unsupervised variant is that the word embedding matrices X and Y are unaligned across both axes. So there is no direct assumption of correspondence between both the languages, but of course, they follow the same assumption that both the representation spaces are isometric. So they propose to first construct two alternative representations, X dash and Y dash, that are aligned across their jth dimension. And these alternative representations can later be used to build an initial dictionary D that aligns their respective vocabularies. In the next phase of self-training or self-learning, they compute the orthogonal mapping by maximizing the similarity for the current dictionary D and then computing the similarity matrix of the mapped embeddings, where they use symmetric weighting to induce a good dictionary. Again, for a more detailed discussion on this approach, please go through Artech's paper referred to in the slide. Let us move on to the next approach. So please allow me to quickly sum up what this approach does. In the interest of time, I would like to go a little faster. This particular work evaluates and compares alignment versus joint training approaches across three different tasks: bilingual lexicon induction, cross-lingual named entity recognition, and unsupervised machine translation. So this particular approach requires one to feed a combined corpus to it. So they train an embedding set, which is a union of both the monolingual embeddings. Here, the embeddings of each language are trained independently using the individual language corpus. So the seed dictionary for this approach can either be provided by the user, or this approach can learn it in an unsupervised manner as well. So this particular approach also learns your projection matrix W based on your dictionary D, thus resulting in a final embedding set in a shared vector space. Initially, this approach generates source, target, and common vocabularies by reallocating them from the combined corpus to their respective spaces. And later, when they generate mappings, they perform alignment refinement to align the source and target embeddings to a common space or same space. So I hope this discussion on the foundations of cross-lingual embeddings and why unsupervised NMT is needed proves to be fruitful for further discussions. And on that note, I will now stop sharing my screen and hand the control over to my colleague Jyotsana to start the discussion on other foundational aspects. Thank you. Jyotsana, please carry on.
Hello, is my screen visible?
Yeah, it is.
Yeah. So my name is Jyotsana. I'm a PhD student working with Professor Pushpak Bhattacharyya in machine translation. So cross-lingual embeddings, denoising autoencoder, and back translation, all these three components are an important part of unsupervised NMT systems, and understanding of these components is required to understand the unsupervised NMT approaches. So I will now, Diptesh explained about cross-lingual embeddings. I will now explain about denoising autoencoders and then back translation. So to understand denoising autoencoders, we should know what are autoencoders first. Autoencoders are an unsupervised learning technique to train neural networks for the task of representation learning. Here, the neural network is designed in such a way that it learns compressed knowledge representation of the original input. As we can see from the figure, that input of the neural network is original sentence, that is x1, x2, x3, x4, x5, and the output is same as the input. There is a hidden layer H1, H2, containing three neurons H1, H2, and H3, which represents the compressed representation of the input. The problem here is formulated as reconstruction of the original input, and the network is trained to minimize the reconstruction error. The autoencoder needs to learn to balance between how to accurately build the reconstruction and not do overfitting. Such models can overfit and just learn can just learn an identity function or just copying of the input. As number of hidden layer increases, the chances of learning an identity function increase. So the number of hidden layer neurons provides the constraint on the amount of information that can travel through the network, and it forces the network to learn compressed form of data. It is important to ensure that autoencoder model is not simply learning to memorize the input, which can be achieved using a control over the number of hidden layer neurons, which works as regularization here. And to address the risk of learning an identity function, there is a different architecture, which is denoising autoencoder. Denoising autoencoder address the risk of learning an identity function by corrupting the input data on purpose. In this diagram, we can see the NX1, NX2 represents the noisy input, and X1, X2, etc. represents the original input. Here, the network is trained to construct the original sentence given a noisy version of it. And when calculating the loss function, it compares the output values to the original input, not with the corrupted input. Because the input and output are not same, the chances of learning to copy gets reduced. And denoising encoder in sequence to sequence architecture learns using an encoder-decoder model. The encoder here learns to represent the noise, learns a representation of the noisy sentence, and the decoder tries to generate the original sentence from the encoder representation of the noisy sentence. Here also the capacity of the encoder and decoder should be handled carefully to still handle the risk of learning to copy. Denoising autoencoder is an important part of UNMT's unsupervised NMT systems, where it helps the model to learn to generate data in that particular language. In NLP applications, a sentence can be corrupted using different types of noises. Some of the common noises are swapping of words, like in a sentence, I go to school. The corrupted sentence can be I too go school. Go and to are swapped with each other. Similarly, some words are removed with certain probability, and some words can be replaced with some other words. So these kind of noises are quite common in NLP when using a denoising autoencoder in NLP applications. Now now coming to back translation, which is also an important part of NMT systems. NMT systems requires a lot of parallel data to get trained. But for all language pairs, we do not have that much amount of parallel corpus availability. Back translation helps in improving the quality of NMT models using additional monolingual resources. In back translation, the target side monolingual data is back translated to source language using a target to source machine translation system. This synthetic data is then used together with parallel data to train the model in source to target direction. It has been shown in literature that back translation works better than forward translation in neural machine translation systems, Because in back translation, the target side data, which the model is learning to generate, is original data, and the source is machine translation and translated text, which makes the system more robust to noisy input, and it learns to generate the original text. In back translation, the training uses the generation of synthetic data happens only once. The generation of synthetic data can be incrementally better by utilizing the current state of the system. So iterative back translation is the process which is inspired by the intuition that a better back translation system will lead to better synthetic corpus and will lead to better final model. In back translation, the process of generating the synthetic data is performed once. Iterative back translation is a method to generate increasingly better synthetic parallel data to train NMT systems. Here, here both the models from source to target and target to source is trained simultaneously. And current state of the trained models is used to generate the synthetic data to train the model in opposite direction. From this diagram, we can see that first a model from language L2 to L1, that is from we consider L2 here as the target language, is L1 is the source language. So model from L2 to L1 is trained using parallel data. Then it is used to generate synthetic data using the target side monolingual data, that is the monolingual data of L2 language. Then this synthetic data is combined with the original parallel data, which is fed in, which is used to train the model in the opposite direction, that is from L1 to L2. Then this model is again used to generate the synthetic data using the L1 language monolingual data. And then again, this synthetic data is combined with the original parallel data and used to train the machine translation system in the opposite direction. This process is repeated until convergence. It plays a very important role in unsupervised NMT. Most state-of-the-art unsupervised NMT approaches uses iterative back translation in the fine-tuning phase, which does not use any parallel data. Hong et al. Also showed that iterative back translation is more beneficial for low resource language. As we can see from this table that for French English, when training using 100K sentences, the baseline NMT is just giving a blue score of 16.7. Using one iteration of back translation, it improves to 22.1. Second iteration gives 22.5, and the third iteration gives 22.6 blue score. So it is also beneficial for low resource language for which the amount of parallel corpus availability is very low. So these are some of the foundational concepts of unsupervised NMT, which are very crucial to understand the different approaches of unsupervised NMT. Now Tamali will explain about different approaches of unsupervised NMT. Handing the stage over to Tamali now. Hello, Tamali.
Are we going to take a 5-minute break?
Yeah, we can take a 10 minutes break here. Then Tamali will continue with unsupervised NMT approaches.
So hi everyone, now we'll be taking a 5-minute break. Say it is 11:45 now. From 11:50, Tamali will be talking about unsupervised NMT approaches. So meanwhile, if you have any questions, you can ask us and we'll try to answer those questions.
There's a doubt here by Birdman. Does the iterative back translation accumulate the model's translation errors? Rudra, am I audible?
Yes, Diptesh.
Acha,
So, Jyotsana, do you want to take the question?
is Jyotsana here at all? Ah, she's here.
Yes. Yes, Jyotsana is here.
Yeah, Rudra, you can answer.
Yes, iterative back translation does accumulate the model's translation errors. So this can be observed. So if you have a translation system which gives you a blue score of say 20, right? And you use monolingual corpus to generate pseudo translations and use it to iteratively train the system, you see some improvements. Whereas if you have a machine translation system which gives you a blue score of say 1 or 2, and you use say iterative back translation to generate pseudo parallel sentences and train the model, there'll be hardly any improvements, or there'll be a drop in performance. So back translation works when you have a decent quality or decent quality machine translation system in hand, and you want to improve it further. So does that answer your question?
Yeah.
Thanks. So hello, Budman. Thanks for the question. I'm not sure if there's a difference between on-the-fly back translation and online back translation. Probably we'll have to, yeah, we'll look at the literature and see.
A question for the icon organizers, the meeting host. Can I please speak to you for a second?
Yes.
Hi. So a master student from our lab at CFILT would like to join the session. I hope it's okay if I share the link with them.
Yes, sure. The link
Thank you.
the link for this tutorial should also be available on the icon web page.
Okay. Thank you so much. Thank you.
So hi everyone, Tamali will be starting the presentation now.
Hi. Is my screen visible?
Yes, Tamali, it is. Yeah.
Okay. Good morning, everyone. I'm here to explain different UMT approaches. I will first start with unsupervised NMT, then GAN for UNMT, then unsupervised SMT, and then I will end with hybrid UMT. It started with two concurrent papers in ICLR 2018, which showed that it is possible to train an NMT model without any parallel data. One was by Arteche et al. And second one was by Lampel et al. These two approaches are very similar in nature and give similar blue scores. Though similar, they differ with each other in some ways. Now let's explore what they did. There are mainly three components of UNMT, which meets three purposes of UNMT. First is bilingual embedding, which projects word embeddings of both the languages in the same embedding space. Diptesh already explained cross-lingual embedding techniques for this. The second one is language modeling, which helps the model to encode and generate sentences. Denoising, masking of words, and some strategies to learn language model characteristics. Language models can be trained either through initialization or through iterative training. The third one is iterative back translation. It bridges the gap in encoder sentence representation between source and target languages. Let me explain this in the next slide. Here is an example of sentence representations of language pair L1 and L2. The first image shows the encoder sentence representations after language model pre-training and before back translation. And the second one is a visualization of encoder sentence representation after back translation. Here, black dots means L1 encoder sentence representation, and the red dots means L2 sentence representation. Before back translation, they form two clusters, and after back translation, they are mixed well. This is an example of simple UNMT architecture. Particularly, this one is proposed by Arteche et al. UNMT architectures are basically encoder-decoder architecture with a bilingual embedding layer. This should have a dual structure to train source to target and target to source together, with partially or fully sharing their models. Sharing helps the sentence representations to be language independent. Like here, in Arteche's approach, encoder is shared and decoders are language specific. Now let's see how this Arteche's architecture is trained in an unsupervised way. Arteche's approach is to train its architecture iteratively for n iterations. Jyotsana already explained denoising and back translation. Here for each iteration, they perform denoising and back translation for both source and target languages. Let me explain it with an example. For each iteration, the first step is denoising of source sentences. Denoising not only helps the model to get the language properties, but also helps the encoder to handle word order divergence between source and target languages. Because shuffle is also a type of noise. We give noisy source sentence as input and train it with the original source sentence as a output of source decoder. It updates shared encoder and source decoder weights, keeping the target decoder weights unchanged. Similarly, denoising is done for target sentences, which trains shared encoder and target decoder. We give a noisy target sentence as input and train it with the original target sentence from the target decoder. As shared encoder encodes both source and target languages during denoising, we expect the encoder to encode these two languages in other steps. Jyotsana already explained back translation. Now we generate back translated data from source to target using shared encoder and target decoder. And target to source using shared encoder and source decoder. Training is not performed during generation, so it is not trainable. Then we train the model with back translated data from source to target and target to source. Encoder was able to encode both the languages. Now it is getting trained to produce representations which are language independent. It helps the target decoder, for example, to take encoder output of source language. Though this decoder was so far trained with only input of noisy target data. In the beginning, I mentioned there are two approaches. Arteshi et al. I explained. Now let's see how different the Lampel et al.'s approach is. Lampel et al. Use shared encoder and shared decoder. Both are shared. Number two, Lampel et al. Initialize training with word-by-word translation. I will explain it in next few slides. And and number three, we use a language discriminator to discriminate encoder representations with respect to language. It challenges the language invariance nature of encoder representations. I will explain this in next subsection. With unsupervised dictionary induction using unsupervised cross-lingual embedding, it is easy to generate word-by-word translated sentence. This way, we can generate synthetic target translation from source monolingual corpus. Can we use this synthetic parallel corpus to train an empty model? Yes, we can use this synthetic data to train along with denoising and back translation. These are some blue scores as a result from these two papers. They use WMT14 and WMT16 dataset for English French and English German. So they got improvement over simple nearest neighbor word-to-word replacement. Now, GAN for UNMT. Remember I said I will explain discriminator in the next subsection. So here I explain how to use GAN to enhance the language invariance. We also explain how to share a module partially. GAN is a clever way of training two submodels, generator model and discriminator model. It is designed in such a way that the discriminator tries to discriminate real versus synthetic data, and generator tries to generate more realistic synthetic data. In this way, they challenge each other to improve their ability. In case of UNMT, shared encoder is the generator, and an extra discriminator module is attached with it to discriminate encoder representations language-wise. In this way, the encoder can be trained to be more language invariant. Now we know language invariance can be imposed by adding a discriminator. This made us free to experiment with sharing and non-sharing of module. Let's think what are the possible encoder-decoder combinations we can have. Can we have the fourth one? No, because there is no common point to map both the languages in the same latent space. But this is possible. Now, how to share the latent space? This is how encoder and decoder can be shared partially, and latent space can be shared. That is by sharing some layers. Here only top one layer is shared, here 2, 3, and now the whole encoder is shared. And this is how an architecture with weight sharing layers may look like. Wang et al. Showed in their paper that sharing only one layer improves the blue for English French, English German, and English Chinese language pairs. When sharing is more than one layer, then blue score drop. This drop is more in case of distant language pairs like English Chinese. They used three discriminator with it to impose language invariance. Local GAN DL to ensure input language invariance of encoder representations. Global GAN DG1 and DG2 ensured input language invariance of output sentences. This is what they showed as result. They got improvement over their baseline systems. They showed result for a distant language pairs, which is English Chinese, which the previous papers did not show. Previous two papers were dealing only with closely related language pairs. So now unsupervised SMT. There are some components of SMT like phrase table language model, reordering model, word phrase penalty tuning. So in order to train this without any parallel data, the challenges are phrase table induction and unsupervised tuning. And if we can meet these challenges, we can improve it with iterative refinement and subword information. So how to induce phrase table in USMT? For that, we first need to create phrase level embedding, that is n-gram embedding. So how to do that? We know what to make is trained this way. Given a word W and never word C, we update embedding for both W and C. Like C for all neighboring words in a window. Here, to train n-gram embedding, the change we make is not to update neighbors embedding while training. In order to enforce unigram invariance, the context C, which is always corresponds to unigram, are not updated. Like this. Now we have phrase embeddings. To get translation probability, now we have to think that how to get the translation probabilities. For that, we take 100 nearest neighbors of other languages and calculate probability from distance with source word compared with distance between source word and other neighbors. Suppose we want the translation of that black dot in the image, then we will consider its 100 closest red point. We will not consider black points here, and apply softmax function over the cosine similarity of the respective embeddings. Now, how to do unsupervised tuning? One approach is using MART tuning with synthetic data, but that is not very appreciated. So another better approach is to train it with cyclic loss and language model loss. Cyclic loss encourages the translation of a sentence to be close to original sentence itself. And LM loss prefers a fluent translation in the target side. Iterative refinement. To improve the quality, we do something similar to back translation in NMT, that is iterative refinement. To accelerate the process, a subset of data can be used for translation model without fine-tuning the language model, because it is not needed. It can be trained with monolingual data only. We all know the need for subword information in MT, like in the chat section of Pushpak sir, it is already discussed that subword level information is very crucial for MT people. So we want to favor phrase translation candidates that are similar at the character level. To utilize this, additional weights are added to the initial phrase tables, like lexical weighting. But unlike lexical weightings, it uses character level similarity function instead of word translation probability. This scoring function selects a phrase that maximizes the product of similarity of source word with their lexically closest word in the target phrase. USMT produced this blue score when tested on WMT14 and WMT16 datasets. They beat previous UNMT approaches for some blue scores. Then hybrid UMT. We can combine UNMT and USMT in two ways. One is USMT followed by UNMT and UNMT followed by USMT. This is quite obvious, but what to do? Which one to select? We can either initialize a UNMT system with the pseudo parallel data produced by SMT, or we can initialize USMT system with the pseudo parallel data produced by UNMT. So Lampel et al. Showed that the USMT followed by UNMT produced a better result. The reason is quite intuitive, that we know SMT gives better adequacy and NMT gives better fluency. So to improve overall translation quality, we first need to improve adequacy, then improve fluency. So we take this one, USMT followed by UNMT over UNMT followed by USMT. That's all from my side. Now to explain different pre-training strategies, I would like to call Rudra.
And thanks, Tamali. So yeah, Birdman, related regarding your question. So it turns out the term on-the-fly back translation was used by RTHA. And if you look at their approach and the approach being followed in the literature, so there's not much of a difference. So on-the-fly back translation and online back translation are almost one and the same. Okay, and yeah, let me share my screen. So is my screen visible?
Yes, Rudra.
Yeah. So till now we have looked at some of the earlier approaches for unsupervised neural machine translation or unsupervised machine translation in general. So we'll now look at some of the pre-training approaches for unsupervised NMT. So in this section, we'll be talking about 5 methods: XLM, CMLM, MAS, BART, and MBART. So I'll be talking about XLM, CMLM, MAS, and Jyotsana will be covering the section on BART and MBART. So XLM is cross-lingual language model pre-training. So and it was published in NeurIPS 2019. So before directly jumping into say the XLM approach, let's take a step back. So if you look at any typical deep learning module, right? So we have the encoder and then we have the decoder. So the input to the encoder will be input symbol. It could be characters, words, phrases, or sentences. It passes through a lookup table and then the actual encoder and gets an encoder representation. That encoder representation is fed as input to the decoder. Now the decoder could be a simple classifier if you are looking at classification techniques, or it could be a generator if the task is say machine translation or any natural language generation task. Now it turns out we usually encode symbols as one-not representations in NLP. So when we present this one-not representation as input, the first layer of the encoder acts kind of a lookup table, because for every word, irrespective of the position in which it appears, we get a position independent representation. And if you look at the embedding space of this lookup table, here we see there's no notion of similarity between similar words or similar symbols. Yeah. So there was a groundbreaking work by Inton with the greedy layer-wise pre-training of neural networks, where the goal was to iteratively pre-train different layers of the neural network using unlabeled data. So this led to the work of Colobert, Weston, Mikolov, and Bengio, where the goal was to pre-train this lookup table or learn better word embeddings. The intuition is, if you look at this embedding space, here we see a topic emerging from this embedding space, like money, bank, and finance. They are appearing nearby. You have weather, rain, humidity, they are appearing nearby. So when we initialize the lookup table with such embeddings which reflect some notion of similarity across words, the end NLP task would be benefited. The next obvious question is, okay, can we initialize the encoder also, or we pre-train the encoder? So what are we expecting when we pre-train the encoder, say for tasks like machine translation? Say if I have a sentence, right? I went to the market and I went to the grocery store. We want these two sentences to be having eye similarity or to be near to each other in this encoder representation space. Similarly, say India won the match versus India defeated Australia. They should be near to each other. And this is what approaches like Elmo, BERT, even XLM does. So the general framework of unsupervised neural machine translation using language model pre-training follows two stages. So in the pre-training stage, we take the monolingual corpus from the two languages and train the language model. Once we have trained the language model, we copy the weights of the language model and use it to initialize the weights of the NMT system. And using L1 monolingual corpus and L2 monolingual corpus, we fine-tune the model. So for fine-tuning, iterative back translation is usually employed. Some approaches also include denoising autoencoding in the fine-tuning stage. So going to XLM pre-training. So XLM uses transformer encoders. Since, okay, given a sentence, say I went to the market, what it does is it randomly picks certain words to be matched. So in this sentence, the word went and the word market are matched. And these are fed as input to the encoder. The encoder has to predict the missing words. Since the encoder is a transformer module, it has no information. It cannot implicitly represent the position. So for that, we use positional encoding. So this is the first word, second word, third word, fourth word, fifth word, and so on. So there are different ways of encoding the position information. It could be sinusoidal position encoding, or we could treat positional encoding as learning embedding itself. And then we have the embedding with respect to the corresponding word. And if you are training, jointly training on multiple languages, we can optionally have a language layer. So if I have two languages, say English and Hindi, I can represent English as 0 and Hindi as 1. And the corresponding language embedding is summed up with the embedding, the word embedding and the positional encoding and fed to the encoder. Now, coming to the fine-tuning stage, so it employs two fine-tuning objectives. One is iterative back translation and denoising autoencoding. So in iterative back translation, as discussed earlier, what happens is I take, if the task is for English to Hindi unsupervised NMT, I take an English sentence, pass it through the encoder, get the corresponding Hindi translation. I take the Hindi translation as input to the model and ask the model to generate the correct English sentence. So this is, and in denoising autoencoding, what we do is we take an input sentence, we randomly mass certain words in the input sentence or shuffle the order of the words in the input sentence and ask the model to generate the correct sentence. So we can think that denoising autoencoding is helping, or it's helping training the decoder model better, or it's kind of acting like a language model compared, if we compare it with phrase-based SMT. Now, looking at the results, so in their paper, they compare their results with the previous state-of-the-art approaches, which is NMT, phrase-based SMT, and phrase-based SMT plus NMT. These are unsupervised NMT approaches. And they test their system for 3 language pairs: English French, English German, and English Romanian. They compare their mass language modeling objective with causal language modeling objective. So causal language modeling objective is the usual language modeling objective where given the context, we try to predict the next word. Here they try out different ways of initialization. So here the first column stands for encoder and the second column stands for decoder. What if we initialize only the decoder with the pre-trained CLM weights? What happens if we initialize the decoder with only MLM weights? What if we initialize the encoder and decoder with weights learned using CLM? And the same goes, what if we initialize the encoder and decoder with pre-trained weights from MLM objective? They consistently observe improvements over both initializing the word embedding layer versus initializing the encoder and decoder using CLM objective for almost all language pairs. So pre-training using MLM objective really helps, and the results are obtained are also statistically significant. Now I'll look at another approach, cross-lingual mass language modeling approach. And this was published in EM-NLP, IJS-NLP 2019. So taking a step backwards, so if you look at the original MLM objective used in BERT by Devlin, so basically what happens is, given a sentence, we match certain words in the input sentence and ask the model to predict the missing words. But there's a major limitation with this approach, especially when we want to train unsupervised NMT. Because currently what we are doing is we have English monolingual corpus, Hindi monolingual corpus, we combine them, take English sentences, try to predict the missing word, Hindi sentences, try to predict the missing words. Just this joint training on combined corpus, it's not a strong signal to learn good multilingual representations, right? I mean, I apologize for the background noise. Say if I have the sentence, I went to the market and मैं बाजार गया था, there's nothing in the model which ensures that, say, market and bazaar are synonyms or translations and they should have similar representations. So to address this limitation in their paper, they propose to provide explicit cross-lingual signals to the model while pre-training. So this is how their cross-lingual mass language modeling objective looks like. Say if the input sentence is मैं बाजार गया था, I'll mask this, if the selected phrase is bazaar gaya tha, I'll mask this phrase and ask the model to generate the corresponding translation in the other language, which is went to the market in English. But there's one issue which we need to address. Okay, they've obtained n-gram phrase translations as discussed earlier by Tamali, and MLM tries to predict the missing word. So I know that this position contains a missing word and I have to predict the corresponding token. But here we have a mismatch between source and target phrase length, right? For example, here we have 3 words in the input sentence, which are masked. and there are 4 words which needs to be generated, and MLM cannot explicitly achieve it. So for that, what they do is they go back to phrase-based SMT and look at IBM model 2. So in IBM model 2, given X1 to XL input source tokens, and if I want, what's the probability of generating Y1 to YM, the target tokens. So this probability basically depends on the alignment probability and the translation probability. Now introducing this IBM model 2 in the objective. So the loss function of CMLM becomes this. So here epsilon is what's the probability that the generated translation consists of M tokens. And then we take the summation over the alignment probability and the translation probability. And when we take the gradients, we see that the gradient depends on the alignment and the translation probabilities. So as long as we can obtain some values for this alignment probability and translation probability, we are good to go. So the way they obtain the alignment probabilities, I have cross-lingual word embeddings or cross-lingual byte pair embeddings. I'll take the cosine similarity between them and use it to approximate the alignment probability. Now for translation probability, what I do is I have the source token xi. I pass it through the encoder, get the contextual embedding representation, and pass it through the decoder, which is nothing but a linear layer followed by softmax. That will help me in getting the translation probability. Now we know how to obtain the alignment probability and the translation probability. We are good to go. We can train the model. So this is how the overall algorithm looks like. They alternate between CMLM and MLM objective. So in traditional MLM objective, which was used by XLM, what you do is you take a source sentence, randomly match certain words, and ask the model to predict the missing words. Here, what they do is 50% of the times they'll select a phrase and replace it with the corresponding translation. So in a way, they are generating some kind of pseudo code switch sentences. And then the usual MLM objective is applied. In CMLM objective, what they do is I select the phrase, match the phrase, and ask the model to generate the corresponding translation in the other language. So they alternate between these two objectives. And even here, they report the results on English, French, German English, and Romanian English. So, and they compare it with the previous state of the art approaches. So, which was XLM in this case. They consistently observe improvements using their cross-lingual match language modeling objective, indicating that as we provide more and more anchor points to the model will be able to learn better multilingual or language agnostic representation, which should benefit unsupervised NMT. So in their paper, they also performed some ablation studies to find out the relative importance between CMLM, MLM. So what they did was they just trained the model using CMLM objective without MLM objective. So they observed some drop in the blue score, like 34.8 to 34.1 and so on. And then they dropped the translation prediction task entirely. Because of this, there was a huge drop in performance. So CMLM plus MLM minus the translation prediction task, it basically boils down to you have a source sentence. I take a phrase, mask it, and ask the model to generate the phrase in the same language, not in the other language. So you can see that since we are removing the explicit cross-lingual signal, the model is not able to learn better language agnostic representations. And lastly, what they do is instead of masking the phrases, what if I mask words? So which is basically MLM. Even here, they observe significant drop in performance. Next, we'll look at MAS. MAS is nothing but masked sequence to sequence pre-training. And this appeared in ICML 2019. So the major limitation of XLM or CMLM was in unsupervised NMT, the end goal is to generate a sequence. But in the pre-training, we are training the model to generate the missing word. So there's a strong disconnect between the pre-training objective and the fine-tuning objective. Now, can I minimize this disconnect? Or can I ensure that the pre-training objective somewhat closely resembles the fine-tuning objective? So they extend XLM objective to include text segments. Let me take an example. So we have this sentence, right? I went to the market. Let's say I apply byte pair segmentation and I get this phrase. I went to the, and the word market is split into two tokens, MAR and KET. Now I randomly select the and MAR as the tokens to be masked. I feed this as input to the encoder. Now the encoder has to generate the missing phrase, the MAR. And if you closely look at the input to the decoder, right, we give the previous masked word, like the previous word to the masked first masked token, the was 2, and 2 is given as input to generate the next the is given as input to generate the next token, MAR. So this is the mask pre-training strategy. And unlike XLM, which had iterative back translation and denoising autoencoding, so they employ only iterative back translation. The argument there was, since the pre-training phase already trains the decoder, we don't have to, or training with denoising autoencoding objective won't help much. And looking at the results reported in the paper, even here they compare their results with XLM for English, French, English, German, and English, Romanian. And they observe consistently larger improvements on all these language pairs. And mass has a set of hyperparameters, and we'll have to look at how different hyperparameter values could make or break the system. The first set of hyperparameter is the percentage of n-gram tokens in a sentence to be masked, also known as the masking length. So if the sentence is I went to the market yesterday night, and let's say if I chose the masking percentage of n-gram token to be 50%, then the phrase selected would be say to the market yesterday. So in the paper, they keep the default value to be 50%. Say if we keep it as 90%, then one set of input could be just the word I, and everything in the sentence is masked. Additionally, what they do is, let's say I select this sentence or select the phrase to the market yesterday. Not all the words in this phrase are masked. Only K% of the tokens are selected for masking. L% of the tokens are replaced by random tokens. They call it as replace probability. And the remaining tokens, they are kept as it is. In the paper, the default values are kept to be 80%, 10%, and 10%. Now let's look at how different hyperparameter values could affect the UNMT model. First, let's look at a role of masking length. So as you can see, as we observe the increase the masking length, we observe that the perplexity drops and also the blue score increases. Now, after around 60 to 70%, if we increase the masking percentage, the perplexity increases and the blue score drops. This is intuitive, right? Because here I have a sentence. Now, if I select 80% of the tokens to be selected for masking, then it's a very harder challenge for the model to reconstruct the sentence. Say if we look at this sentence, right? I went to the market yesterday night. And if I mask went to the market yesterday, and the only tokens are I and night, there's literally many possible sentence constructions, and which the model will be confused. So I will have to strike a good balance between the masking length percentage, and 40 to 70% seems somewhat good. Now let's look at the other set of hyperparameters. Let's take this example sentence. Say मैं तो आपके घर से चाय का पत्ती मांगने आई हूँ, and we select 50% of the consecutive tokens for masking, and let's say the selected n-gram phrase is घर से चाय का पत्ती. Now 80% of the tokens are selected for masking, 10% are randomly replaced. So here we see 3 tokens are masked, and 1 token is kept as it is, and another token ka is randomly replaced with a word say pina. Now this is given as input to the model, and the model has to generate this missing phrase ghar se chai ka patti. So for this, what we did was we tried with different configurations, like what if the masking percentage is less but the retaining percentage is high, or what if masking percentage and retaining percentage are somewhat equal and the tokens randomly replaced is kept low. What if we increase the masking length percentage, or what if we increase the randomly replaced words percentage. Now looking at the graph, here we see this plot the test set perplexity during the pre-training. So if you look at the top 2 lines, so these are the lines where the masking percentage is greater. So not the masking percentage, the word keeping percentage is greater than 40%. The perplexity is low, indicating that the model is not able to connect the two languages together. And the model is efficiently behaving as an autoencoder. As we increase the masking length, or as we increase the word replacement probability, we see the touch set perplexity drops down significantly. And this is in log scale. So a general comment regarding the selection what should be the ideal values. So if you are training for unsupervised NMT system, it's better to go with what is being reported in the paper, like 80% masking, 10% retain, 10% randomly replacement. Or even if you increase the masking length to 90%, it helps improve the performance. Now, if the task is not say machine translation, but if it is for some kind of other cross-lingual task, say sentiment analysis or named entity recognition, you can alternate between should we have an higher percentage of masking percentage, or should we have a higher percentage of words which are randomly replaced. And going back to the task, the configuration which achieves the lowest test set perplexity is the one where the word random replacement percentage is high. Even though the test set perplexity is high, but if you look at the blue score, there's not much of a difference. So for unsupervised NMT, it's better to go with higher probability of masking percentage. But if it is other cross-lingual tests, you can juggle between these two parameters. And also there's another set of hyperparameter or conscious choice made by the authors. Say, we'll go back to the same sentence. I went to the market yesterday night, and we select this phrase to the market yesterday. Now the input to the encoder is I went, and then the mass tokens and night. But the input to the decoder is went to the market. Now, why should we give the input to the decoder as went to the market, and why not feed in I went to the market yesterday night as it is? So this is similar to training and denoising autoencoder. They call this approach as feed. And the other is why mask consecutive tokens and not discrete tokens. So they did some experiments. So this is how the feeding input tokens looks like. So they observe a significant drop in performance using both discrete and feed, whereas using their n-gram masking, they observe larger improvements, which was also reinforced by our earlier approach CMLM. So it turns out that for sequence tasks like unsupervised neural machine translation, masking an entire phrase is more beneficial compared to masking discrete tokens. Okay, now I'll hand over the stage to Jyotsana to cover the material on BART and MBART. Thanks.
Hello, am I audible?
Yes, you are.
Yeah. Thanks, Rudra. So Rudra explained different language model objectives for pre-training in unsupervised NMT, that is XLM, CMLM, and MAS, and also explain in very detail about the hyperparameters, different hyperparameters that are utilized in those pre-training objectives. So BART, that similar to XLM and MAS, it also pre-trains a sequence-to-sequence architecture using a denoising objective. BART was published, this paper was published in ACL 2020, and there is an extension of this using multilingual denoising pre-training, which is MBART. So first we'll discuss about what is BART. So it basically, it is basically similar to XLM and MAS, which pre-trains the system using a denoising objective. The difference lies in what the noise function is and how it gets trained. As in mass objective, we have seen that it basically masks a span of text and tries to predict that particular masked span given the masked sentence. In BART, what the difference is, BART tries to predict the entire target sentence given a masked version of it. XLM basically operates on masked language modeling objective, and masked pre-trains encoder and decoder such that encoder is given a noisy version that is a masked span, a sentence with a masked span, and decoder learns to generate the masked fragment. And BART, unlike XLM and MAS, the BART works at multi-sentence level. So here we will refer it as one instance. So they use sentence permutation as well in the noise function, and it learns to generate the entire target sentence given the noisy version of that particular instance. So they perform different sets of experiments for various tasks using different noise functions. So some of them I'm going to explain the different possible noise functions can be. So consider the sentence instance, my name is John, I go to school daily. So different kinds of noise function is token mask. First one is token masking, where some tokens from the sentence is masked with certain probability. That is, my dash is John, so name is masked here, and I go to school daily. Go and to both tokens are masked. Token deletion. Some of the tokens from the instance is deleted with certain probability. What happens in text infilling is a span of token is masked and replaced with a single mask. So in this example, my name is John, name is masked and replaced with a single token. I go to school daily, to school daily is masked and replaced with a single token. And BART works as at multi-sentence level. So, and a document, an instance here contains multiple sentences. So for corrupting a particular instance, sentence permutation is also one of the possibility. That is randomly shuffle the sentence within a particular instance. And the document rotation can also be one of the possible noise. That is, in this, a token is chosen randomly and the document or an instance is rotated such that it starts with that particular token. So in this example, name token is selected and the document is rotated such that name is the first token. So name is John, I go to school, then my. So this represents the corrupted version of the sentence, my name, instance, my name is John, I go to school daily. Lewis et al. Performed different experiments with different noise functions for various tasks and found that text filling plus sentence permutation is the best performing noise across different tasks, in which they remove in which uh, they remove span of text and replace the mask tokens, and thus select the mask 30% of the words in each instance by randomly sampling a span length, and they also permute the order of sentences within a particular instance. Yeah, in their paper of BART, they don't show many results for unsupervised NMT, but it was later utilized by MBART, that is multilingual BART, which BART here refers to bidirectional and autoregressive transformers. The BART pre-training objective was later utilized by Liu et al. MBART is a sequence-to-sequence denoising autoencoder, which pre-train using large-scale monolingual corpora in many languages using the BART objective. And fine-tuning is so for unsupervised experiments, they pre-train using BART objective using many languages, and fine-tuning is performed using iterative back translation. So in this table, for English German and English Romanian, we can see that MBART is performing better than XLM and MAS pre-training objectives. For English German and English Romanian, the pre-training using BART objective is only trained using source and target languages, that is English and German for English German and English and Romanian for English Romanian. But for the major thing to observe here is for dissimilar language pairs, that is English Nepali and English Sinhalese. When we train using XLM, the blue score is very poor. That is for English Nepali, it is 0.5. But when using MBAT objective, that is pre-trained using multiple languages. So here it is, the MBAT is pre-trained using 25 languages, inclusive of English, Nepali, and Sinhalese. So we can see that the results using MBAT is far better than using XLM. They also claim that MBAT also generalizes well for the languages not even seen during the training. So here we discussed different types of, till now we discussed different types of unsupervised NMT approaches, and also the role of language model pre-training and different types of language model pre-training objectives, which are utilized in literature for training unsupervised NMT systems. So now we'll discuss about when unsupervised NMT does not work. So there are many factors impacting the quality of unsupervised NMT systems. So we'll be discussing majorly these two, about the content of these two papers and our experience of unsupervised NMT. So domain similarity is an important factor for the performance of unsupervised NMT systems. In high resource language pairs, availability of monolingual data of the same domain is still feasible, but it is not feasible thing for low resource languages. From this table, we can see that when both source and target monolingual data is from same domain, that is for English German, when the data is from newswire domain, same domain, the blue score is 23.3. But when it is from different domain, that is English is from newswire and German is from politics, the blue score decreases with a huge amount, that is 11.5. So the current state of the art architectures of unsupervised NMT is very sensitive to the similarity of domains of the monolingual data of both source and target languages. And this happens because of different distributions of the data. Same is the case for dissimilar language pairs where the distribution of the data is very different. And almost all the architectures of all the approaches of unsupervised NMT which we have discussed are based on learning a shared encoder and decoder. So when the data distribution of source and target languages is very different, it is very difficult to learn the shared representation. And the second thing is, they also, Grassa et al. Also experimented with different kinds of initializations. So they say that better initialization leads to reasonable NMT model in the fine-tuning stage. But when the model is started with bad initialization, unsupervised NMT cannot build a reasonable NMT model starting from no matter how much data is used in the fine-tuning training. So from this diagram, the dotted lines represent when the initialization training was performed only using 10K sentences, and solid line here represents where the initialization training was performed using 20 million sentences. We can see that from this diagram that when we start with a very poor initialization, the fine-tuning phase is not able to learn good translation no matter how much data is being used in the fine-tuning stage. So and the final model correlates well with the initialization quality. Grassa et al. Also showed that it is not beneficial to use more monolingual training data on one side. That is often the case when translating from English to low resource languages or low resource languages to English. In figure, it is clear that when using large data on one side, it is not helpful in unsupervised NMT. Here the target side data is fixed to 20 million sentences, and the solid line represents where the source and target number of source and target sentences are same. And dotted line represents where it is unbalanced, and the number of sentences of source side is given on the x-axis. We can see that if the data is unbalanced, it does not help in improving the performance of unsupervised NMT systems. So if the training is performed using severely unbalanced data, the distribution of the smaller side will be much sparser than that of the larger side. The network learns to generalize more on the smaller data, thus it learns very different distributions of each side, which is again a very challenging task for a shared model to learn. So, and one, yes, and the other fact, one important fact, cross-lingual, the quality of cross-lingual embeddings is also an important factor in the final, in the qua- uh, in the quality of final unsupervised NMT systems. Now Rudra will explain about the importance of quality of cross-lingual embeddings in unsupervised NMT. Handing over to Rudra now.
Thanks, Jyotsana. Should we take a 15-minute break now?
Yes.
Hello, ma'am. There are two questions, one from Birdman and one from Asha. One question is denoising method the major difference between BART and mass? And the second question is how to decide the initialization quality.
So the difference between mass and BART is in the denoising part and the training part. So mass basically learns to generate the masked phrase only, and BART basically learns to generate the full text. So the output of the decoder is full text in BART, but output of the decoder is the masked fragment in mass. And BART works at the multi-sentence level, and there is a difference in denoising function also.
Okay, ma'am. Second question was how to decide the initialization quality.
So we don't decide the initialization quality. It is by initialization, what I meant here is the quality after we train the pre-training, after the pre-training stage. That is after. So most of so the general framework which Rudra discussed is first the model is pre-trained using a denoising objective, that is either XLM, MAS or BART or CMLM. Then the fine-tuning stage involves iterative back translation and denoising optionally. So the initialization here refers to the stage after pre-training. Yeah, so the quality
Okay.
of the system after the pre-training stage.
Yeah, thanks, Jyotsana. Also, one way to look at the initialization quality is monitor the test set validation set perplexity. So we have access to parallel corpus, the validation set parallel corpus. So after every iteration during the pre-training phase, we can monitor what's the perplexity looks like. If we see that after some iteration, the perplexity is increasing, probably the model is overfitting or there's something wrong in the model, and that's where we need to stop it. So I guess XLM does that. They look at if the per test set, validation set perplexity does not increase after certain number of iterations, they abruptly stop the pre-training phase.
Okay, sir. There is one more question from Birdman. Can we say that perplexity of 140 is okay for stopping pre-training?
So here the perplexity is relative, right? For different languages, the perplexity would be different. Say if you are looking at analytical languages or isolating languages, we can achieve a very low perplexity. Whereas if you are looking at agglutinative languages, the perplexity will usually be very high because of the choices. So the way or the way it's done is, say if I'm training for say English to Hindi, I have a validation set parallel corpus, English to Hindi and Hindi to English. I calculate the validation set perplexity for every epoch. And what we expect is the perplexity has to drop after every iteration. But if the perplexity is not dropping, or if we see a sudden jump in perplexity, and if that trend continues, say for 3 to 4 epochs, then there is something wrong in the training, or the model might be overfitting. So that's when we stop the pre-training process stage. I mean, it's difficult to say what exactly, I mean, what the perplexity or what actually the perplexity value should be. I guess one close approximation is, say, if we can train a language model for the language of interest, we have the LDOT data and see how, say, a neural language model performs, or what's the perplexity of that neural language model. And based on that, we can compare what's the perplexity achieved by our pre-training strategy. But yeah, it's difficult to say if perplexity of 140 is okay, because it depends on the languages we are considering.
Thank you, sir.
So Jyotsana, Tamali, Diptesh, do you want to add anything?
No, I think I'm good.
Yeah, since it's been a long session, I guess we'll meet at 1 o'clock. So from 1 o'clock, we'll look at the quality of cross-lingual word embeddings and how it could have, or why the quality of cross-lingual word embeddings matters for unsupervised NMT, and also some of our initial findings for Indian languages to Indian languages unsupervised NMT. Shall we begin the session now?
Okay.
Yeah, okay, let me reshare my screen. Okay, so we have looked at many of the unsupervised NMT approaches, and we have also seen when unsupervised NMT approaches work and when it fails, like language relatedness, the domain difference, and so on. Now we look at another dimension, which is the quality of cross-lingual word embeddings. Just a recap. So if you look at the first, one of the earlier approaches for unsupervised NMT by Lampel et al., the way they went with training the unsupervised NMT system was they trained monolingual word embeddings on the two languages, and they obtain cross-lingual word embeddings in an unsupervised manner. This can also be obtained if you, in a supervised manner if you have bilingual dictionary. Now, they initialize the lookup table of the encoder with these cross-lingual word embeddings, and they are not updated during training. And the success of their approach relied on the quality of cross-lingual word embeddings. So yeah, there were other factors also, but yeah, quality of cross-lingual word embeddings played a prominent role. Now, just a recap of cross-lingual representations. So you have English word embedding space and French word embedding space. And you see that the word embedding space are nicely uh, aligned such that semantically similar words are closer to each other. And I want to align the English embedding space with the French embedding space. The intuition is learning a simple rotation matrix will help me align the two embedding spaces. This is what most of the cross-lingual word embedding approaches try to achieve. Now, why is the quality quotient? Yeah, taking a step backwards again. If you look at the encode-decode paradigm used for machine translation, right? We have the input sentence. The input sentence is fed as input to the encoder. And here the encoder comprises of the lookup table and the encoder layer. So the lookup table could be the word embedding lookup table or the byte pair encoding embedding lookup table. And we get a sentence representation. So this, let us call it as the encoder representation space. Now, by looking at this sentence representation, the decoder has to generate the correct translation. Now, during pre-training stage, what we are doing is, I take an L1 sentence, send it through the encoder, get the representation, and ask the model to regenerate the L1 sentence itself. So we are sending a noisy version of the L1 sentence. Similarly, I take an L2 sentence, uh, noise it, add some noise to it, send the noisy version of the L2 sentence, get a sentence encoder sentence representation, pass it through the decoder and reconstruct the original L2 sentence. So this is fine for closely related languages, but for say distant languages, so there's nothing in this the network architecture or the objective which we are trying to optimize, right? Which ensures that, say, if we have parallel sentence in both the languages, they'll be having similar sentence representations. That's not guaranteed. But what if we initialize the encoder lookup table with cross-lingual word embeddings? Say if the sentence is I went to the market and May bazaar gaya tha in Hindi, and we had a cross-lingual word embedding such that the word embedding of I and the word embedding of May, the word embedding of bazaar and the word embedding of market, they are close to each other. Then we can at least ensure that probably the sentence representation of I went to the market and May bazaar gaya tha will be closer to each other. Now, what happens during iterative back translation in fine tuning is I feed in I went to the market, get the encoder representation, and ask the model to generate the translation, not reconstruct the original sentence. If, say, the sentence representation of I went to the market and May bazaar gaya tha were closer to each other, then the decoder will be able to generate the correct translation. If the encoder representation is very bad, then there's hardly any chance that the model will be able to generate the correct translation. I mean, let's forget about the correct sentence. The model might not be able to generate even a single word correctly. So this is why we'll have to focus on the quality of cross-lingual word embeddings. And also another reason being, so we talked about the CMLM approach, right? Cross-lingual match language modeling approach. So in their approach, they were generating the translation candidates, and the translation candidates were generated using cross-lingual word embeddings. So if the cross-lingual word embedding quality is bad, then the generated translation quality, translated candidate will be bad, and the model might not be able to learn anything. Now let's look at how existing, say, cross-lingual word embedding approaches perform for different language pairs. So in the first block, we have European language pairs, and here we have English to Indian language pairs. And this is JOM. So JOM is one approach to obtain cross-lingual word embeddings. And this results are for bilingual lexical induction test. Say given an Hindi word, I get the word embedding, find the nearest neighbor in the English space. Let's say I take top 10 nearest neighbors and see if the translation candidate appears in the top 10 candidates. So in the paper, they report the result for precision at 1. So if the top 1 candidate is the correct translation or not. And this is the results from supervised approach, not unsupervised approach, which is usually what we say in unsupervised NMT, training cross-lingual word embeddings in an unsupervised manner. So for English to European language pairs, as we see, the bilingual precision at 1 is very good, greater than 75%. And yeah, if we instead of precision at 1, if we calculate precision at 10, probably it will be in the order of 90s. Whereas for Indian languages, it's below 50%. And as the languages say, if the language is morphologically rich, as is the case with Tamil, the precision drops even further. And this is supervised cross-lingual word embeddings. If we go with unsupervised cross-lingual word embeddings, say the precision at 1 might not even cross 20 or 30%. Now, so reiterating again why we have to focus on the quality of cross-lingual word embeddings, how it matters. So these are the results reported by Lampel et al. So what they did was they trained unsupervised cross-lingual word embeddings and used it to perform word-by-word translation. So I take the English sentence. For every English word, I find the top one nearest, top one candidate in French and use it as the translation. Just by simple word-to-word translation, we see English to French 8.54, French to English around 17%, German to English 15%. So this was on one data set. If you look at on WMT, even in WMT, they report very good results just by simple word-to-word translation. Now, what if we try to do something similar, say for English to Hindi, which have, say, large monolingual corpus available to train these word embeddings? See, the blue score is very bad, 1.2, 2.1. So if we start, say, if we initialize our model with such pre-trained word embeddings, the improvements we expect to get, say, in unsupervised NMT would be very limited, because 1.2, yeah, a disclaimer here, we would have this number is very unfair because 1.2, 2.1 blue score is word-to-word translation. And since English to Hindi have different word order, yeah, the blue score calculation is a bit off. But if we still compare it with English French and English German, the blue score is very poor. So what we are trying to push forward is, if the quality of cross-lingual word embedding is bad, then we will not be able to gain much improvements from unsupervised NMT methods. One of the reason being, okay, some of the papers which we have missed in our current tutorial is, recently there's some work on using code mixing to improve unsupervised NMT systems. So what they do is they generate synthetic code mix sentences. And the way they generate synthetic code mix sentences is via cross-lingual word embeddings. I mean, I'll just go back a bit. So we have this sentence, right? मैं बाजार गया था. If I know that बाजार गया था maps to went to the market, why don't I give may went to the market as input to the model and train the model? So this is what code mix pre-training is. And generation of such sentences relies entirely on cross-lingual word embeddings. So if the cross-lingual word embedding is bad, so instead of went to the market, I could get some arbitrary sequence of English words, which does not make sense. And if I train my unsupervised NMT system using such code mix sentences, there is no way the model will be able to learn good translations. Coming back to the slides. Yeah. So we'll have to focus on learning good cross-lingual word embeddings, not just between English to Indic languages, but also between Indic to Indic languages. Because learning cross-lingual word embeddings between, say, agglutinative languages like Tamil, Malayalam, Kannada, or Telugu, it's much more challenging. And also, majority of the NLP approaches, they operate at the subword level. Now, can we learn cross-lingual word embeddings at the subword level? Because these unsupervised NMT system, they take the subword tokens as input, not words as input. So if we want to take advantage of cross-lingual word embeddings, how do we learn the embeddings at the subword level? Now we'll move on to the next session, which is unsupervised NMT for Indic languages. These are some of our initial findings. So, I mean, the very first question, why did we choose Indic languages and not just report results on English, French, or English, German, or English, Romanian? Because we see a spectrum of languages in the Indic subcontinent. So it's a testbed for research on multilinguality. So this table reflects the lexical similarity between languages. What I meant by lexical similarity is the cognate overlap across languages. Let's not look at Hindi Punjabi results because there's some transliteration error. But if you look at other Indo-Aryan languages like Bengali, Gujarati, Hindi, and Marathi, we see that in these say shades, significant cognate between Gujarati and Hindi, and also Bengali to a certain extent. However, the cognate overlap between Indo-Aryan and Dravidian languages is limited, and across Dravidian languages is also limited. So now if you want to have work on languages which are having high lexical similarity, we can just focus on the Indo-Aryan language family and test our models. If we want to see our models perform across languages, we can take languages from the Indo-Aryan language family and Dravidian language family and see how the models behave. Or if we want to test on, say, how unsupervised and empty models behave for agglutinative language to agglutinative language translation, then you have Dravidian languages and Marathi where we can see how the unsupervised NMT systems behave. So we don't, I mean, we have a spectrum of languages. So whatever language divergence we want to isolate, we can isolate and study. And also low resources, low resource. Yeah, if we compare the say quantity of monolingual corpus available for Indic languages, it's no way comparable to English or a few other European languages. We still have a decent amount of monolingual corpus available for Hindi. To a certain extent, with the continued efforts from Anup and Mitesh et al., we have some good quality monolingual corpus available for Bangla, Punjabi, Malayalam, and so on. Whereas at the other spectrum, we have languages like Odia, Assamese, Maghai, Bhojpuri, where we hardly have any monolingual corpus available. Say for Bhojpuri, if we look for monolingual corpus available, we hardly get around 1 lakh sentences. Now imagine retraining, say, XLM or BERT using these 1 lakh sentences. So we cannot expect much from the model, right? Because the model is huge. We have very low corpus. There's high chance of overfitting, and the model might not learn anything. So we have a spectrum of low resourcesness. If we want to work on resource-rich languages, we can choose this pair. If we want to work on resource-rich and resource-poor language, we can take some of the languages from this group, and we can focus on Oriya, Assamese, Maghai, Bhojpuri, and so on as the low resource languages. Yeah, not just low resourceness, also the spectrum of morphological complexity. So here I'm just say we look at the type token ratio. So type is the total number of unique words in a corpus, and token is the total number of words in the corpus. The general idea is if type token ratio is very less, then there's a high chance that the language is morphologically poor. It's more of an analytical or isolating language. Whereas if type token ratio is very large, then it's an agglutinative language. So we have a spectrum of morphological complexity as discussed earlier. So if we want to focus more on morphologically or morphologically rich languages, we can focus on the Dravidian languages. If we want to focus on morphologically poor languages, we can look at Hindi, Gujarati, Punjabi, and so on. Now, these are some of our initial findings. So what we did was we grouped the languages into different groups based on their lexical relatedness. I apologize for the background noise. So high lexical relatedness, medium lexical relatedness, and no lexical relatedness. And if you look at the blue score with pre-training and fine-tuning for both source to target and target to source, we observe that lexical relatedness plays a crucial role. If the lexical relatedness is high, then the UNMT system performs decently well. And the results are not comparable with the European language part, where they report blue score in the order of 35, 40s, but we get a blue score of around 10 to 12 blue score points. Whereas for medium, if the lexical relatedness is less, the blue score is less than 1. So indicating that existing UNMT systems cannot be used directly for Indic languages, there's something additional which we need to perform. Yeah. So what we can conclude is, yeah, existing unsupervised NMT systems, they fail for Indic languages. For closely related languages or lexically related languages, we observe some decent blue scores. And also, if we consider morphological richness, that adds more complexity to the model. As we saw from the earlier results mentioned by PB sir, that if you are training an NMT system or a machine translation system across, I mean, within Indo-Aryan language family, the blue score is usually good. With say from Indo-Aryan to Dravidian language family, the blue score drops. Across Dravidian language family, the drop is much larger. So yeah, this adds more complexity to the unsupervised NMT system. And what we ask the community from this tutorial is, yeah, please focus more on Indian languages. We need more research on Indic languages. So with this, I hand over the stage to Jyotsana and Tamali for the concluding remarks.
Hello, sir. There is a question.
Yes.
Does the code switch pre-training work similar to the jointly cross-lingual pre-training?
Yes. So so if you look at this jointly, just a minute. Yeah. So the question is jointly cross-lingual pre-training, right? So
Yes, sir.
in jointly cross-lingual pre-training, what we do is we have a monolingual corpus from the two languages, and we train the model jointly. And there's no explicit cross-lingual signal coming. So for lexically related languages like English, French, or English, Spanish, because of the high vocabulary overlap, the cross-lingual signal is implicit. But if we consider distant languages like English, Japanese, English, Hindi, or English, Tamil, or English, Malayalam, so there's no explicit signal, right? So it's like training two different language models with shared encoder and decoder with minimal cross-lingual signal being transferred across languages. So we expect code switch pre-training to work better compared to jointly cross-lingual pre-training. And that's what been reported in the literature also. So probably we'll update the slides with the references which we forgot to add here, where they use this code switch pre-training for UNMT. And that really helps for distant languages specifically.
Thank you, sir.
Hi, am I audible?
Yes, yes, you are.
Yeah, so this is towards the end of the tutorial. So we discussed various paradigms of machine translation, that is rule-based machine translation, statistical machine translation, neural machine translation, and very detailed discussion on unsupervised neural machine translation. We also discussed in detail about various the foundational concepts required to grasp an understanding of unsupervised NMT paradigms. Discussed in detail about various unsupervised NMT approaches with promising results for some language pairs. Rudra discussed about various approaches which utilizes various language model pre-training objectives, that is XLM, MAS, CMLM, BART, MBART. After that, we discussed when unsupervised NMT does not work. So we have shown that it is for dissimilar language pairs, it needs more attention to create good models for unsupervised NMT. We also presented brief results for various Indic languages with various domains of related and unrelated language pairs. A more thorough and deep research is needed for improving the quality of unsupervised NMT systems. So what is the future of unsupervised NMT? So in the last 3 years, unsupervised NMT gained quite a lot of attention of researchers. Progress in unsupervised NMT has been very impressive. It even achieved performance near its supervised counterparts for some language pairs. But the current state of the art approaches performs poorly for realistic low resource language pairs and dissimilar language pairs. There is a room for improvement in unsupervised NMT for low resource language pairs making the unsupervised NMT robust to dissimilar domains and making it robust to the dissimilarity between language pairs. We have also seen that unsupervised NMT suffers when the fine-tuning starts from a poor initialization phase. There is a scope of improvement in improving language model pre-training for dissimilar language pairs and dissimilar domains. We have also seen that cross-lingual embeddings are an important part of unsupervised NMT systems, and for distinct language pairs or dissimilar language pairs, the quality of cross-lingual word embeddings have shown to be poor. There is a need to improve existing methods such that they become robust to dissimilarity between language pairs and give good results for realistic low resource scenarios. So now we are open for questions. If you have any questions, please you can unmute yourself and ask. And the tutorial is uploaded on GitHub. You can find the slides and other details on this link. Any questions from anyone?
Well, if there are no questions, then maybe the organizers can take a call on ending the session or something like that. There is one new message. Thank you so much, Birdman.
Thank you, sir. So should we end the session, sir?
Yes, I think if there are no more questions, we really should. And as a concluding remark, I would like to thank all the audience members and all my colleagues, including my supervisor, Professor Pushpak Bhattacharyya, for conducting this session and especially for introducing all of us so gracefully. I really liked this experience, and as always, ICON is really good to us, all of us, every year. So thank you, organizers. Thank you, Professor Asif. Thank you, Professor Pushpak, and all my colleagues. And of course, not last but not the least, thank you, the audience members. Yeah.
Thank you, sir. So we are ending this session. If nobody have no questions, thank you, everyone.
Thanks. Thank you so much. Bye, everyone.
Yeah. So just before ending, thanks everyone. Hello.
Yeah, Rudra, you're audible. Yeah.
Yes. So in case you have any questions, you can contact us on the links provided here. We'll also uploading the slides on GitHub, and also we'll be sharing with the organizers. So feel free to contact us anytime if you have any questions.
Yeah. I think that should be okay. Okay, everyone. In that case, we'll all probably take your leave.
So I just a question to the icon organizers. Hello.
Yes, sir. Yes, sir. Yes,
Yeah.
sir. Yes.
So how
Yes,
do
sir.
we send the final slides with you guys, like, and yeah,
But-
I mean, what's the next set of procedure?
okay, sir. Give me 5 seconds. Just.
Yeah, sure.
Yeah. Hi, everyone.
Hi.
Yeah. This is Soumitra. So, for slides, we can do one thing. Maybe we can put it up on the icon website itself. Okay, or else we can send it to all like all who attended. But I think it would be better if we can put it up on website, because not all
Yeah,
have
because
registered. Or yes.
yes. So last time what happened was we were asked to send the slides
Mhm.
to the organizers,
Okay.
and the organizers had uploaded the slides in the
Yes,
icon website also.
Right. So yes, you can. So we can follow the same procedure this time also. Okay, so you can send. Yes, you can send the slides to the volunteers for that session. So you must be having their email IDs, right?
Sure.
So we
Yeah.
will collect
So
from all the volunteers of the session, the other sessions as well, and we will
okay.
upload it on the website.
Okay, sure. That's great.
Yeah. Okay.
So yeah, Jafar. So there are a couple of references to be added, especially the code mixing one. So we'll add those references and send the final slides. So you can find it on the icon website, as well as, or what I'll do is I'll just write down the link where you can find the slides.
Yes.
Say by tomorrow end of day, you should be able to find the uploaded slides in this link.
Okay.
So if you have any further doubts, would there be any way in which you could contact you or the team?
Yeah, sure. Oh, sorry. In the slides, we forgot to mention our mail IDs. Yeah, we'll add our mail IDs and share it with you.
Okay, sir. Thank you so much. Thank you so much for conducting this tutorial as well.
Uh, Thanks.
Rudra sir, or my